a technological achievement, but a manufacturing one as well. AST SpaceMobile operates nearly 500,000 square feet of manufacturing and operations facilities and employs a workforce of nearly 1,800 people. The company is 95% vertically integrated, maintaining strict United States control over the entire manufacturing process. This level of integration allows them to iterate quickly and maintain quality control. We are not just building satellites, we built a new way to manufacture innovative space technology at scale. Bluebird 6 is just the beginning. AST SpaceMobile is on track to launch 45 to 60 satellites by the end of 2026, with launches planned every 1 to 2 months on average. The company has agreements with over 50 mobile network operators globally, representing nearly 3 billion subscribers combined. The vision is clear: global cellular broadband from space, accessible by every smartphone on Earth. Before 2026 began, China launched what may be the most powerful weather satellite ever built. On December 27, 2025, a Long March 3B rocket carried the Fengyun 4C satellite into orbit from the Xichang Satellite Launch Center. It's the third satellite in the Fengyun 4 series, and it represents a generational leap in meteorological observation capability. The main technical specifications have been improved by 2 to 3 times compared to its predecessors. Fengyun 4C carries an unprecedented suite of instruments: 4 different types of Earth observation remote sensing instruments and 2 solar observation instruments. It integrates comprehensive detection capabilities, including multi-channel 2-dimensional imaging, 3-dimensional atmospheric sounding, and lightning mapping. This is not just a weather satellite, it's a complete Earth and space weather observatory. The Advanced Geostationary Radiation Imager is a marvel of engineering. It has reduced its time for full-disk imaging from 15 minutes to just 5 minutes. That means it can scan the entire Earth-facing hemisphere 5 times faster than its predecessor. But the real magic is its sensitivity. It can detect atmospheric temperature changes as fine as 0.02 degrees Celsius from tens of thousands of kilometers away. The Lightning Mapping Imager is capable of capturing 500 frames per second. It identifies lightning events from a data stream of 30 gigabits per second, equivalent to playing back 30 high-definition movies in 1 second. From this torrent of data, it pinpoints every lightning flash, earning its nickname, Keen-Sighted Eyes. This real-time lightning data helps forecasters identify rapidly intensifying thunderstorms and issue earlier warnings. In February 2026, Indian space tech startup Galaxy announced Mission Drishti, a groundbreaking satellite slated for launch later this year. What makes Drishti special isn't just what it sees, but how it thinks. It features the world's first sync-fused optosar architecture, combining 2 different imaging methods on a single satellite. Mission Drishti moves the company closer to providing real-time intelligence from orbit. The sync-fused optosar architecture is revolutionary. One system captures detailed visual images, similar to photographs taken from orbit. The other uses synthetic aperture radar, SAR, to see through clouds, darkness, and even heavy rain. By merging these 2 methods, Drishti can produce consistent, dependable images regardless of weather conditions or time of day. This means no more waiting for clouds to clear. The satellite sees through them. Perhaps the most revolutionary aspect of Drishti is its brain. The satellite is powered by NVIDIA Jetson computing hardware, enabling it to process much of its data directly in space using artificial intelligence. Instead of sending large amounts of raw information back to Earth for processing, a slow and bandwidth-intensive process, Drishti analyzes images in orbit and quickly delivers useful insights. Galaxy envisions even more. Mission Drishti will test the concept of orbital data centers, where multiple satellites work together like a network of computers in space. Such systems could make future satellite networks faster, more reliable, and transform multiple sectors. In agriculture, it could provide faster crop health monitoring. In disaster response, it could map floods and fires in real time, even through clouds. For environmental tracking, it could monitor deforestation with unprecedented reliability and provide persistent, all-weather surveillance. It's invisible, but it's everywhere. Every time you open maps on your phone, every time an airplane lands in low visibility, every time a farmer precisely plants a field, you're using GPS. The Global Positioning System is one of the most critical infrastructures ever built, and in 2026, it's getting an upgrade. On January 27, 2026, SpaceX launched a Falcon 9 carrying the GPS-3 SV09 satellite from Cape Canaveral Space Force Station. This marked the ninth of the next-generation GPS Block 3 satellites launched since 2018. Designed by Lockheed Martin, this satellite is part of an ongoing effort to modernize the entire GPS constellation. What does Block 3 bring to the table? 3 times better positioning accuracy and 8 times stronger anti-jamming capabilities. These improvements benefit everyone, from the military user in a contested environment to the civilian driver navigating city streets. Looking ahead, the Block 3F satellites will introduce the constellation's first fully digital navigation payload. GPS is just one of several global systems. There's Europe's Galileo, Russia's GLONASS, and China's Beidou. Together, they provide redundancy and improved accuracy for users worldwide. When your phone calculates your position, it's likely using signals from multiple constellations. The competition in space-based navigation is healthy, and it benefits everyone. As satellites multiply, traditional radio frequency communication is hitting its limits. Spectrum is congested and bandwidth is finite. The solution? Laser communication. Optical data links enable satellites to rapidly and securely transmit complete data sets in a single burst, a significant improvement over legacy systems. In February 2026, the European Space Agency and Airbus announced a breakthrough. They successfully demonstrated laser communications between an aircraft and a satellite 36,000 kilometers away. The Ultra Air system achieved a bit error-free data rate of 2.6 gigabits per second, maintaining a secure link despite platform movements and vibrations. This breakthrough has both civilian and defense applications. For defense, laser communications provide a secure alternative to radio frequency, with low probability of interception. For civilians, it could enable high-speed data connections for passenger airliners and ships, keeping everyone connected anywhere on the planet. China is quietly building its own massive low-Earth orbit internet constellation. On January 19, 2026, a Long March 12 carrier rocket lifted off carrying the 19th group of SatNet satellites. Developed by Galaxy Space, these satellites use advanced phased array and millimeter wave antennas that are both technologically advanced and cost-effective. Every satellite we launch is another nerve ending in a global nervous system. They watch, they connect, they guide, they protect. In 2026, that nervous system is growing faster than ever. We are moving toward a world where everyone is connected, every storm is predicted, and every part of our planet is understood. The strongest and latest satellites of 2026 aren't just machines. They're the foundation of our collective future. Thank you for watching this journey through the satellite revolution. Comment below. Which of these satellites impresses you most? Subscribe for more space documentaries.
Welcome to this in-depth update from NASA. Today, we explore groundbreaking missions shaping our future. On February 13th, a new crew arrived at the International Space Station. This team replaced astronauts evacuated due to a medical emergency. Meet the crew: Jessica Meir and Jack Hathaway from NASA, Sophie Adenot from France, and Andrei Fedyaev from Russia, pioneers of this historic journey. This crewed flight marks a milestone, the first since Apollo, to orbit the Moon, paving the way for Artemis missions. Weeks of intensive training ensure the crew is prepared. Every detail is practiced for a safe journey. Back on Earth, mission control teams monitor every detail, tracking data, ensuring all systems function perfectly. NASA is also launching 2 new Earth-observing satellites, Strive and Edge, designed to monitor climate change and natural disasters in real time. Strive will focus on extreme environments, providing early warning systems for floods, wildfires, and storms. Edge will monitor long-term climate patterns, offering insights for future missions to the Moon and Mars. Despite these advances, a budget freeze has paused over 15 scientific missions, pending further funding approval. Even the Chandra X-ray Observatory faces delays, as budget constraints force a pause on key science missions. A groundbreaking discovery: ammonia detected on Europa, hinting at possible habitability beneath its ice. The detection of ammonia strongly suggests the presence of a vast subsurface ocean. This discovery fuels hopes of life beyond Earth. scientists now plan follow-up missions to probe deeper. As Artemis takes us back to the moon, Europa exploration may soon follow. Two frontiers of discovery. These new satellites will affect our daily lives, improving disaster response and climate predictions. While new missions excite, funding challenges put some science projects on hold, awaiting further approval. Despite hurdles, NASA forges ahead, building new partnerships, new technologies, and new dreams. Public engagement grows. Students, scientists, and dreamers alike follow every step of NASA's progress. Stay with us on this cosmic journey. NASA will continue to reach for the stars and bring the universe closer to home. Across the globe, audiences are tuning in, inspired by each milestone in NASA's journey. Students everywhere are dreaming bigger. Many now aspire to careers in space exploration. NASA scientists are reaching out, bringing space knowledge to classrooms, fairs, and community events. Mark your calendars. Upcoming launches like Artemis II are set for later this year, a landmark step in space exploration. NASA's success depends on global partnerships. Together, we push beyond boundaries. Each mission pushes technology forward, new materials, new propulsion, and new possibilities. As NASA explores new frontiers, space tourism may also become a reality in the coming decade. NASA's educational programs empower a new generation, offering free courses in STEM fields. With these satellites, we can better understand and act on Earth's climate crisis, ensuring a healthier planet. From the ISS crew to new satellites, every achievement brings us closer to understanding our universe. The future of human spaceflight is vast. Mars, deep space, and beyond, all within our reach. Stay connected with NASA. Visit their website and follow them as we continue reaching for the stars. NASA's ambitions reach far beyond Earth, deep space probes that will one day leave our solar neighborhood. Future missions envision human habitats on Mars, self-sufficient, sustainable, and ready for pioneers. The James Webb Space Telescope is unlocking cosmic secrets, peering back at the universe's earliest moments. Though paused, Chandra's legacy endures, its discoveries reshaping our understanding of black holes and stars. Space research also focuses on astronaut health, understanding how microgravity affects the human body. From space, we see Earth as one, our fragile home, interconnected with every step we take beyond. Women like Jessica Meir and Sophia Adenauer are breaking barriers, leading the way in space. Every mission inspires the next generation, those who will one day reach farther than we ever dreamed. NASA's legacy is built on decades of courage, each mission laying the groundwork for the next. As we look up tonight, remember, NASA is not just about rockets. It's about dreams reaching the stars. Follow NASA online, be part of the journey, and help shape the future of space. Until next time, we continue this adventure, exploring, discovering, and dreaming together. From space, we see our home in new light. Every nation, every ocean, connected in one planet. NASA is also leading in green innovation, developing sustainable technologies for Earth and space. Women engineers are driving innovation at NASA, bringing fresh perspectives to every project. From lunar orbit, Earth looks so fragile, this pale blue dot, uniting us all in one vast cosmos. On the ISS, every day brings new discoveries, from plant growth to materials science, pushing boundaries. Strive and Edge will monitor Earth's health, helping us respond to climate changes before it's too late. NASA's partnerships with private industry accelerate innovation, new rockets, new data, and new possibilities. NASA opens its treasure trove of data to the public, empowering researchers, students, and policymakers alike. In the next decade, space tourism may become a reality, with NASA paving the way. NASA reminds us, our journey is not just about leaving Earth, but about understanding where we fit in this vast universe. By sparking curiosity, NASA inspires kids to ask big questions about space, about Earth, about the future. Every launch takes us one step closer to new worlds, new technologies, and new hope. NASA reminds us that Earth is delicate, Our responsibility to protect it grows with every discovery in space. We need your innovation. As we reach for the stars, we also build a better future here on Earth. NASA promises to keep exploring, keep innovating, and keep dreaming for all of humanity. Thank you for joining us. Until next time, keep looking up, keep dreaming, and keep exploring.
Looking for premium quality proxies at unbeatable prices? You found it with IP Royal. Access over 34 million ethically sourced IPs with lightning-fast speeds and traffic that never expires. Relied on by over 10,000 businesses every day. IP Royal, one of the best price-quality ratio on the market.
This is our home, Earth, the only place in the universe where we know for certain that life exists. Blue oceans, green forests, white clouds, a jewel in the darkness of space. But it wasn't always like this. 4.5 billion years ago, there was no Earth, no continents, no oceans, no life, just a vast cloud of gas and dust spinning slowly in the darkness. Then, something happened. A chain of events so violent, so improbable, that it would create a world capable of nurturing life. This is the story of how Earth was made. Every human who has ever lived has asked the same question. Where did we come from? How did this world, our world, come to be? For most of human history, we had only myths and legends, gods creating worlds from nothing, cosmic eggs hatching. But today we have something better. We have science. And the story it tells is more dramatic, more violent, and more beautiful than any myth. Our planet Earth is a child of the sun. We sprang from the same interstellar cloud of gas and dust that created our parent star. In this documentary, we'll trace the complete story of Earth's formation, from the death of ancient stars that seeded our solar system to the birth of the sun, from the chaotic collisions that built our planet to the giant impact that created the moon, from the arrival of water to the formation of continents. This is the making of a planet. From the first spark of life to the world we know today, let the journey begin.
Our story begins not with Earth, but with the raw materials that would make it. 4.5 billion years ago, our region of the Milky Way was filled with a giant molecular cloud, a vast, cold expanse of gas and dust, stretching for light years. This cloud was 99% hydrogen and helium, with traces of other elements. But those traces were everything. NASA JPL says, this cloud was caught in a shockwave when a nearby star reached the end of its life and exploded. Here's the first miracle. The elements that make up Earth, the silicon in its rocks, the iron in its core, the oxygen in its air, were forged in the hearts of ancient stars. These stars lived and died before our sun was born. When those stars exploded as supernovae, they scattered their enriched remains across the galaxy. Our solar system formed from the ashes of those stellar deaths. The supernova blast caused our birth cloud to spin and heat up, and most of the material in the cloud's compressed center ignited into our sun. Something triggered the collapse. Perhaps the shock wave from a nearby supernova, perhaps a collision. Whatever it was, gravity took over. The cloud began to shrink, spinning faster and faster. As it contracted, it flattened into a disk. At the center, material piled up, pressure building, temperature soaring. A star was about to be born. As the gravity pulled the material into the center, it heated up. Suddenly, the young sun ignited. Some questions seem too big to answer. We answer them anyway.
How do we know a supernova triggered our solar system's formation? The evidence is locked inside ancient meteorites, rocks that have remained unchanged since the birth of the solar system, nearly 5 billion years ago. Scientists studying these meteorites have found isotopic signatures that can only be explained by a supernova explosion occurring just before our solar system began to form. By measuring isotopes, particularly of metals, scientists have identified two distinct asteroid populations that formed in the inner and outer solar system. Meteorites contain evidence of short-lived radioactive isotopes, elements that decay quickly, decaying in just a few million years. For these isotopes to be present, they must have been created very recently. The most likely source, a supernova, exploding in our cosmic neighborhood, seeding the molecular cloud with fresh radioactive material. That supernova gave us more than just a trigger. It gave us the raw materials for Earth itself, the silicon that makes up our rocks, the iron at our core, the oxygen we breathe, the carbon that forms the basis of life. All of it was forged in that stellar explosion, scattered across space and incorporated into our forming solar system. We are, quite literally, made of stardust. The cosmos is within us. We are made of star stuff. Some questions seem too big to answer. We answer them anyway. Around the newborn sun, the remaining gas and dust formed a swirling disk, the protoplanetary disk. For millions of years, this disk was a cosmic carousel of raw material. Dust grains orbited the sun, colliding, sometimes sticking, sometimes shattering. Slowly, almost imperceptibly, the first building blocks of planets began to form. The formation of planets started with dust grains that grew into larger bodies, eventually forming planetesimals, including the primordial Earth. The process was incredibly slow. Dust grains, smaller than a grain of sand, collided and stuck together due to electrostatic forces. Over thousands of years, they grew into pebbles. Pebbles collided to form rocks. And boulders, over millions of years, coalesced into planetesimals. These were the first true building blocks of planets. Planetesimals, or miniature planets, formed from the coalescence of dust, rocks, ice balls, and boulders within the solar system's disk. Once planetesimals reached a certain size, their own gravity began to help. They could now pull in smaller bodies from greater distances. The larger they grew, the faster they grew. This runaway process, over just a few million years, transformed a disk of tiny particles into a swarm of planet-sized objects. Among them, the primordial Earth was taking shape. The stage was set. The raw materials of our world had finally come together, but the journey from dust to a living world was only just beginning. Next, we witnessed the era of bombardment, where fire and stone forged the foundations of life. Stay tuned as we continue The Impossible Explained. Some questions seem too big to answer. We answer them anyway. Some questions seem too big to answer. We answer them anyway. Today, we dive into the violent birth of our world. Earth takes shape. The Earth that emerged from this process was nothing like the planet we know today. It was a hellish world. A ball of molten rock, heated by the energy of countless impacts and the decay of radioactive elements. Its surface was an ocean of magma, churning and bubbling. No continents, no oceans, no atmosphere, just fire and rock. NASA JPL notes, our planet's birth was savage, multiple crashes of particles that liquefied from the violent heat of impact, and then clung together, a molten sphere that grew ever larger with each new collision. The chaos was only the beginning. Inside, something revolutionary was happening. As the molten Earth churned, gravity began to sort its materials. Heavy elements, mostly iron and nickel, sank toward the center. Lighter elements, silicates, floated upward, forming the mantle and eventually the thin crust. This process, called differentiation, happened over millions of years. It gave Earth its layered structure, a dense metallic core, a thick rocky mantle, and a thin outer crust, a blueprint for a living world. As NASA JPL observes, after millions of years, the storm of particles subsided as the last fragments of the birth cloud dispersed. Our planet cooled, but it did not rest. Deep below, the fire still raged. The formation of the core was perhaps the most important event in Earth's early history. As iron sank, it released gravitational energy. This heat would become the engine that drives plate tectonics, volcanism, and crucially, the magnetic field. The magnetic field that protects us from solar radiation. Without it, life would be impossible. Even today, the core remains hot, radioactive elements continuing to stoke its inner fire. NASA JPL adds, beneath the surface today, the fury of Earth's origin rages on. Radioactive elements in the rocks like uranium, thorium, and potassium stoke this inner fire. Our history is written in rock and fire. From a violent youth to the cradle of life we know today, the Earth's foundation was built on chaos. Join us next time as we explore the moon's arrival. Some questions seem too big to answer. We answer them anyway. Some questions seem too big to answer. We answer them anyway. When Apollo astronauts returned from the moon, they brought back something unexpected: rocks. And when scientists analyzed those rocks, they found something astonishing. The moon rocks were nearly identical to Earth rocks in their composition, specifically in their oxygen isotopes. This was a puzzle. If the moon formed separately, it should have a different composition. If it was captured, it should be different. The only explanation? The moon came from Earth itself. The Apollo 11 mission and subsequent Apollo missions brought back lunar rocks that were found to have much in common with Earth rocks,
including similar oxygen isotopes. The leading theory is now widely accepted. About 4.5 billion years ago, when Earth was still young and molten, another planet collided with it. This planet, which scientists call Theia, was about the size of Mars, roughly half Earth's diameter. It struck at an angle, with enormous force. The impact was so violent that both planets were vaporized, their outer layers blasted into space. The collision created a ring of molten rubble that coalesced into the Moon. For thousands of years, Earth was surrounded by a ring of molten rubble, the remains of Theia and Earth's outer layers. Slowly, gravity pulled this material together. Clumps formed. They collided and merged. And over perhaps 100 years, a new body took shape. The Moon was born. It hung close to Earth, much closer than it is today, filling the sky as a gigantic, terrifying, and beautiful sight. This event gave Earth its rapid spin and tilted axis. The Moon's formation wasn't just a dramatic event. It was essential for Earth's future. The Moon's gravity acts as a stabilizer, preventing Earth's axis from wobbling wildly. Without the Moon, our climate would be chaotic, making life far more difficult. The Moon's presence stabilized Earth's environment, setting the stage for life. Some questions seem too big to answer. We answer them anyway. See you in the next chapter.
By 4.4 billion years ago, Earth had settled into its basic structure. At the center, a solid iron inner core, surrounded by a liquid outer core of molten iron and nickel. Above that, the mantle, a 2,900-kilometer thick layer of solid rock that flows like an incredibly slow liquid over geological time. And finally, the crust, a thin, brittle outer shell, ranging from 5 to 70 kilometers thick. Thinner than the skin on an apple. NASA JPL states, lighter elements like silica floated and formed a thin crust, while heavy elements like iron sunk to form the core. The churning of liquid iron in the outer core creates an extraordinary phenomenon: Earth's magnetic field. This field extends thousands of kilometers into space, forming a protective bubble around our planet. It deflects the solar wind, a constant stream of charged particles from the sun, and shields us from harmful cosmic radiation. Without it, Earth's atmosphere would be slowly stripped away, and life would be exposed to deadly radiation. NASA JPL notes, Earth's magnetic field shields the planet from solar radiation, providing a protective environment for life. Mars once had a magnetic field too, but because Mars is smaller than Earth, its core cooled more quickly. About 4 billion years ago, the Martian core solidified, and its magnetic field died. Without that shield, the solar wind slowly stripped away Mars's atmosphere. The planet went from warm and wet to cold and dry. Earth's larger size kept its core hot and kept its atmosphere intact. As stated, Earth avoided a runaway greenhouse effect due to its protective magnetic field, which deflects powerful solar radiation. Between 4.1 and 3.8 billion years ago, the solar system experienced a period of intense chaos. The giant planets, Jupiter and Saturn, migrated, disturbing orbits and sending a hail of asteroids toward the inner solar system. This period is called the Late Heavy Bombardment. Earth and its moon were caught in the crosshairs. The moon's surface, still visible today, bears the scars. Thousands of craters from impacts that would have been catastrophic on Earth. The crust as it formed began to record an extraordinarily violent period of solar system history. Earth was hit just as hard as the moon during this period. But where are the craters? While the moon's surface preserves scars, Earth's surface is constantly recycled by plate tectonics, volcanism, and erosion. These processes have erased almost all evidence of this violent period. But we know it happened, because we can see it on the moon. As scientists observed, the more meteorite impacts, the older a surface was. This was true not just on the moon, but on all the inner planets. Earth's internal engine continues to churn, keeping our world alive and our atmosphere intact. Some questions seem too big to answer. We answer them anyway. Join us at Concrete Hustle 01 for more stories of the impossible explained.
For decades, scientists debated the origin of Earth's water. Did it come from comets, delivered during the Late Heavy Bombardment? Or was it released from Earth's interior, trapped in minerals since the planet's formation? The answer, we now know, is both. Comets brought some water, but volcanic outgassing, the release of steam from erupting volcanoes, brought much more. Volcanic outgassing, the release of steam from erupting volcanoes, brought much more water to the surface than we once imagined. As volcanoes exhaled water vapor, it gathered into clouds, and the atmosphere became saturated. Volcanoes helped create the ocean. After water vapor they exhaled gathered into clouds, and rain began to fall. As Earth cooled, water vapor in the atmosphere began to condense. For millions of years, it rained. Not gentle showers, but torrential downpours that lasted for eons. The rain filled the lowest basins, forming the first oceans. By 4.4 billion years ago, Earth was covered in water, with only scattered volcanic islands breaking the surface. NASA JPL scientists confirm that water vapor they exhaled gathered into clouds, and rain began to fall. The first oceans were fresh water, but as rain fell on the newly formed continents, it changed. As rain fell on the continents, it dissolved minerals from the rocks, especially salt. Rivers carried these dissolved minerals to the sea. Over millions of years, the oceans became salty. The same process continues today. Every river carries salt to the sea, and the ocean's salinity is maintained by a delicate balance. As the script says, water dissolves minerals from the rocks. Gradually, the ocean's fresh water became salty. Some questions seem too big to answer. We answer them anyway. Follow at Concrete Hustles 01 for more.
Some questions seem too big to answer. We answer them anyway. 4 billion years ago, tiny islands of crust, cratons, formed the cores of our modern continents. Found in Western Australia and Greenland, this ancient silica-rich rock floated to the surface, creating the first stable ground on a changing Earth. 3.8 billion years ago, the crust cracked. Driven by internal heat, plate tectonics began building, reshaping, and recycling our continents in a constant dance of creation. But our survival depends on an invisible shield. Earth's magnetic field deflects the solar wind, preventing our atmosphere from being stripped away into the void. Without it, Earth would be like Mars, a cold, dry desert. Our core's heat keeps this shield active, making life possible where others are barren. The aurora is the visible proof of our protection. I'm your narrator, and this is the impossible explained. At Concrete Hustle 01.
Why is Earth so special? One reason is its position in the solar system. Earth orbits in the habitable zone, the narrow region where temperatures allow liquid water to exist. Venus, closer to the Sun, is a hellish 460 degrees Celsius. Mars, farther out, is a frozen desert. Earth is just right. It's a bit like the Goldilocks story. She tasted one porridge, and it was too cold. That's like Mars. She then tasted another. That was too hot. That's like Venus. Then she tasted the baby bear's porridge, and that was just right. And that's what Earth is now. Size matters. If Earth were smaller, its core would have cooled, its magnetic field would have died, and it would have lost its atmosphere, like Mars. If Earth were larger, its gravity would be stronger, possibly pulling in a thick, crushing atmosphere like Venus. Earth's size is perfect. The Earth has exactly the same components as the Sun. But from early on, there was one thing which made Earth different.
AI is here, ready to lead the way. Stand out and build in-demand Gen AI skills with Coursera. Reshape the way you work with AI and take your career to the next level. Explore more at Coursera.org.
It alone had a large satellite. Perhaps the most remarkable feature of Earth is the carbon cycle, a self-regulating system that has kept our planet's temperature stable for billions of years. Volcanoes release carbon dioxide. Rain dissolves it, forming weak acid that weathers rocks. Rivers carry the dissolved carbon to the ocean. There, marine organisms use it to build shells. When they die, they sink, locking carbon away in seafloor sediments. Subduction eventually returns carbon to the mantle, completing a cycle that takes millions of years. The carbon cycle helps maintain Earth's habitability. Think about what had to happen for Earth to exist. A star had to explode, seeding our region with heavy elements. A cloud had to collapse at just the right moment. Jupiter had to migrate. A Mars-sized planet had to hit us at exactly the right angle to create our moon. Water had to arrive. The core had to stay hot. The carbon cycle had to establish itself. The chain of events is so unlikely, so improbable, that it almost seems miraculous. The Earth's surface is in constant motion. As continents collide, they create great mountain ranges, which influence our climate and shape life. With 100 billion stars in our galaxy alone, surely there must be other Earths out there. Planets with the right size, position, and composition. We found thousands of exoplanets. Some are inhabitable zones. Some are rocky. But none yet show the complex interplay that makes Earth special. Are we alone? We don't know. But the quest to understand our planet and the potential for life elsewhere in the universe continues. 4.5 billion years of cosmic accidents, all leading to this, a blue marble hanging in the darkness, teeming with life. We are made of the dust of exploded stars. We are children of the Theia impact. We are products of the carbon cycle. We are Earth, and Earth is us. That's here. That's home. That's us. On it, everyone you love, everyone you know, lived out their lives. Thank you for joining us. If this documentary inspired you, share it. Comment below what part of Earth's formation amazed you most.
Out there in the vast darkness of the universe, nearly 2.5 million light-years away from Earth, lies a massive spiral galaxy, Andromeda. Bigger than our Milky Way, containing nearly 1 trillion stars, it is our closest galactic neighbor and our future destiny. Spanning approximately 220,000 light-years across, its majestic spiral arms are factories of star formation, burning with the light of new suns. At its heart lies a dense core, packed with ancient stars and a supermassive black hole exceeding the mass of our own sun by millions of times. It is not alone. Andromeda commands a fleet of satellite dwarf galaxies, like M32 and M110, caught in its immense gravitational pull. While most of the universe expands away from us, Andromeda is different. It is hurtling towards the Milky Way at 110 kilometers per second. In about 4.5 billion years, our two galaxies will meet in a cosmic dance of gravity, reshaping the night sky of any world watching. This will not be a destruction, but a merger. A new, massive elliptical galaxy will be born from the chaos, often called Milkomeda. The space between stars is so vast that individual collisions are unlikely, but the view from Earth would be a spectacular light show lasting millions of years. Until then, Andromeda remains a beautiful silent giant in our night sky, a reminder of the dynamic and ever-changing cosmos we call home.
Imagine floating in the vast darkness of space, surrounded by billions of stars. Among them exists a small but extraordinary system, our solar system. Our cosmic home is filled with planets, moons, asteroids, and mysteries beyond imagination. Today, we begin an incredible journey from the blazing sun to the icy edges of deep space. The solar system consists of the sun and everything bound to it by gravity. This includes 8 planets, dwarf planets, over 200 moons, millions of asteroids, and countless comets. All of them orbit the sun in a delicate gravitational balance. Scientists believe the solar system formed about 4.6 billion years ago from a giant cloud of gas and dust. Gravity pulled this material together, forming the sun at the center and planets from the leftover debris. The sun is a massive ball of hot plasma. It produces energy through nuclear fusion, turning hydrogen into helium. This energy provides light and heat to all planets in our system. NASA launched the Parker Solar Probe to study the sun up close. It helps scientists understand solar storms, flares, and space weather that can affect Earth. Mercury is the closest planet to the sun. It has no atmosphere to trap heat, causing extreme temperatures from scorching hot to freezing cold. NASA's MESSENGER orbited Mercury and discovered water ice in shadowed craters. The ESA and JAXA mission BepiColombo is now studying its magnetic field and surface. Venus, often called Earth's twin, is similar in size but extremely hot due to a dense toxic atmosphere. Its surface temperature can melt lead. The Soviet Venera 7 was the first spacecraft to land on another planet. NASA's Magellan mapped Venus using radar, revealing its mountainous terrain. Earth is the only known planet with life. It has liquid water, breathable air, and a magnetic field that shields us from harmful radiation. Thousands of satellites orbit Earth for communication, navigation, weather monitoring, and research. The International Space Station allows astronauts to live and work in microgravity. Earth's moon stabilizes our planet's tilt and affects ocean tides. Its surface is covered with craters and plains called Maria. In 1969, Apollo 11 successfully landed humans on the moon, marking a historic achievement in space exploration. NASA's Artemis missions aim to return humans to the moon and establish a long-term presence for exploration and research. Mars, the red planet, shows evidence of ancient rivers and lakes. Scientists believe it may have supported microbial life billions of years ago. The Curiosity rover discovered organic molecules on Mars and provided evidence of past water, paving the way for further exploration. The Perseverance rover is currently collecting rock samples to return to Earth, searching for signs of ancient life. Ingenuity, the small helicopter on Mars, made the first powered flight on another planet, testing future aerial exploration. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky objects left over from the solar system's formation. The OSIRIS-REx mission collected samples from the asteroid Bennu and successfully returned them to Earth for analysis. Jupiter is the largest planet in the solar system and acts as a gravitational shield, protecting inner planets from asteroids. NASA's Juno mission studies Jupiter's atmosphere, gravity, and magnetic field, providing insight into its formation. Jupiter has more than 90 moons. Europa is one of the most intriguing, with a subsurface ocean that could harbor life. Saturn is famous for its beautiful rings made of ice and rock particles orbiting the planet. The Cassini-Huygens mission revealed water geysers on Enceladus and methane lakes on Titan, expanding our knowledge of potential life beyond Earth. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and a thick nitrogen-rich atmosphere. Uranus rotates on its side, making it unique among planets, with extreme seasons lasting decades. Voyager 2 is the only spacecraft to have visited Uranus, providing the first detailed images of the planet. Neptune is the farthest planet from the Sun, known for its intense winds and deep blue color. Voyager 2 gave us our first close view of Neptune, including its stormy atmosphere and unique moons. Pluto, a dwarf planet in the Kuiper Belt, has a thin atmosphere and icy surface features. NASA's New Horizons mission revealed Pluto's ice mountains, glaciers, and a heart-shaped region, surprising scientists worldwide. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies and dwarf planets, remnants from the early solar system. Far beyond the Kuiper Belt is the Oort cloud, a vast shell of icy objects at the edge of the Sun's gravitational influence. Comets are icy bodies that develop glowing tails when approaching the Sun, providing valuable information about the early solar system. The Rosetta mission successfully landed a probe on a comet, studying its composition and activity in detail. Voyager 1 and 2 traveled beyond the outer planets, exploring Jupiter, Saturn, Uranus, and Neptune, and are now in interstellar space. Voyager 1 carries the Golden Record, containing sounds and greetings from Earth, a message for any extraterrestrial life it may encounter. Space exploration helps us understand life, planetary evolution, climate, and develop technology that benefits humanity. Scientists track asteroids and comets to protect Earth from potential impacts, using advanced telescopes and early warning systems. Space telescopes allow astronomers to study distant galaxies, stars, and exoplanets beyond our solar system. Thousands of exoplanets have been discovered orbiting other stars, revealing worlds very different from our own. Plans are underway to send humans to Mars in the future, aiming for long-term research and possible colonization. Private companies like SpaceX and Blue Origin are advancing space travel, making exploration faster and more accessible. Humans may one day build colonies on the Moon, Mars, or even space habitats orbiting Earth. Scientists search for life on Mars, Europa, Enceladus, and Titan, hoping to answer whether we are alone in the universe. Our solar system is just a tiny part of the Milky Way galaxy, which itself is one of billions of galaxies in the universe. Our solar system is vast, dynamic, and full of mysteries. The journey of space exploration continues, and the future of discovery has only just begun.
In the silent depths of space, beyond Earth's familiar blue horizon, lies a mysterious red world, Mars. For centuries, Mars has captured human imagination, inspiring myths, science fiction, and groundbreaking exploration. Mars is about half the size of Earth, with weaker gravity and a thin atmosphere made mostly of carbon dioxide. It is home to Olympus Mons, the largest volcano in the solar system, towering nearly 3 times higher than Mount Everest. Valles Marineris stretches over 4,000 kilometers, a canyon system so vast it would span across entire continents on Earth. Planet-wide dust storms can engulf Mars for weeks, reshaping its surface and darkening its skies. Scientists believe that billions of years ago, liquid water once flowed across Mars. Ancient Mars may have been warmer and wetter, possibly even capable of supporting microbial life. Humanity's journey to Mars began in the 1960s, with ambitious robotic missions sent across millions of kilometers. Rovers have explored its dusty plains, drilling rocks and sending invaluable data back to Earth. Standing on Mars, the sky appears butterscotch-colored, and the sun looks smaller than from Earth. Mars has polar ice caps made of water and carbon dioxide ice, growing and shrinking with the seasons. Radar data suggests frozen water may still exist beneath the surface. Space agencies plan future missions to send humans to Mars, aiming to build sustainable habitats. Astronauts would face extreme cold, radiation, and isolation, but the rewards could redefine humanity's future. One day, Mars may become humanity's second home. The red planet continues to challenge us, inspire us, and remind us that exploration is part of who we are.
December 1972. Gene Cernan climbed the ladder of the lunar module, took one last look at the desolate beauty of the moon, and spoke words that would echo for generations. "We leave as we came, and God willing as we shall return." Then he stepped inside. The hatch closed, and for 50 years the moon sat silent, waiting. No human footsteps, no voices. Just the whisper of micrometeorites and the slow turning of the lunar dust. But the waiting is almost over. For the first time in half a century, humans are going back. This is Artemis II, the first crewed mission of NASA's Artemis program. Not a landing, not yet, but something just as important, a proving ground. 4 astronauts will climb aboard the Orion spacecraft, ride the most powerful rocket ever built, and travel 250,000 miles to the moon and back. They won't land, but they'll do something no humans have done since 1972. They'll see the moon up close, with their own eyes, and bring the rest of us along for the ride. Why now? After 50 years, why go back? Because the moon is more than a destination. It's a proving ground, a place to test the technologies, the systems, the human endurance that will one day take us to Mars. It's a symbol of what we can achieve when we work together. And in a world that often feels divided, Artemis reminds us that we're capable of something greater. We're capable of reaching for the stars. In this documentary, we'll follow the entire Artemis II mission, from the final preparations on Earth to the moment of launch. From the journey to the moon to the historic flyby of the far side, from the return to Earth to the triumphant splashdown, this is the story of the mission that brings humanity back to the moon. At the heart of Artemis II is a monster. The Space Launch System, SLS for short, is the most powerful rocket ever built. Standing 98 meters tall, it's taller than the Statue of Liberty. When it launches, its 4 RS-25 engines and 2 solid rocket boosters will generate 8.8 million pounds of thrust, more than the Saturn V that took Apollo to the moon. It's a machine of almost incomprehensible power. The 4 RS-25 engines at the base are recycled from the Space Shuttle program, but upgraded, improved, pushed harder than ever before. They burn a mixture of liquid hydrogen and liquid oxygen at temperatures so cold they'd freeze your blood instantly. The fuel is pumped at such pressure that the turbo pumps could drain an Olympic swimming pool in 25 seconds. These engines are the product of decades of engineering refinement. Strapped to the sides are the 2 solid rocket boosters, each one longer than a football field. They provide 75% of the rocket's thrust at liftoff. Once they've burned through their fuel, about 2 minutes after launch, they'll separate and fall back to Earth, where recovery ships will pull them from the ocean for reuse. Nothing goes to waste. The orange core stage is the backbone of the rocket. It holds 2.6 million liters of propellant, enough to fill 10 Olympic swimming pools. At liftoff, it weighs over 2,500 tons. Most of that is fuel. By the time it separates from the upper stage, 8 minutes later, it will be empty, falling away to burn up in the atmosphere.
It's a one-use wonder, sacrificed for the mission. Above the core stage sits the upper stage, the ICPS. Once the boosters and core stage have done their job, this stage takes over, pushing Orion out of Earth's orbit and toward the moon. It's powered by a single engine, a version of the RL-10 that's been used for decades. Reliable, proven, ready for one last job before it's discarded. 4 humans, 1 mission. The first international crew to venture beyond low Earth orbit. 3 Americans, 1 Canadian. Together, they carry the hopes of not just their nations, but of all humanity. Meet the crew of Artemis II. First, the commander, Reed Wiseman, a veteran of a previous space station mission, a naval aviator, a test pilot, the kind of calm, decisive leader you want at the helm when things go wrong. He's flown once before, spent 165 days in space, done 3 spacewalks. Now he leads the most ambitious mission in a generation. The pilot, Victor Glover, a naval aviator, a test pilot, and a veteran of the space station. He'll be the one flying Orion, manually piloting the capsule during critical maneuvers. He's also making history as the first African American to travel to the moon. When he looks out the window at the lunar surface, he'll carry the hopes of millions who dreamed of this moment. Mission Specialist, Christina Koch. She holds the record for the longest single spaceflight by a woman, 328 days on the International Space Station. She's done 6 spacewalks. She's an engineer, a physicist, and now she's going to the moon. When Artemis III lands, she's in line to be the first woman to walk on the lunar surface. But first, she has to prove the systems work. And finally, Mission Specialist, Jeremy Hansen. He's making history as the first Canadian and the first non-American to travel beyond low Earth orbit. A fighter pilot, a veteran of the Royal Canadian Air Force, he's been training for this moment for years. When he sees the moon from Orion's window, he won't just be representing Canada, he'll be representing every nation that dreams of the stars. For 2 years, this crew has trained together. They've hiked through Iceland, learning to read landscapes like geologists. They've practiced emergency drills in simulators, rehearsing every possible failure. They've spent countless hours in the pool, practicing spacewalks they won't actually do, because on Artemis II there are no spacewalks. But the training builds trust, builds teamwork, builds the bond that will keep them alive 250,000 miles from home. The crew's home for 10 days is Orion. At first glance, it looks like an Apollo capsule, the same cone shape that brought astronauts home in the 60s and 70s. But inside, it's a 21st century spacecraft, advanced computers, modern displays, a toilet, something Apollo didn't have, and enough room for 4 people to live, work, and sleep during their journey to the moon and back. Below the capsule is the European Service Module, built by the European Space Agency. It's the workhorse of the mission. It provides electricity from its 4 solar arrays. It holds the fuel for the engines. It carries the water and oxygen the crew will breathe. And at the end of the mission, it will be jettisoned to burn up in the atmosphere, sacrificing itself so the crew can come home. Inside, Orion is cramped but functional. 4 seats, 2 in front, 2 behind. The commander and pilot sit up front with a bank of displays showing everything from trajectory to life support. The 2 mission specialists sit behind, monitoring systems and preparing for observations. There's a small galley for food, a toilet behind a curtain, and sleeping bags that attach to the walls. For 10 days, this is home. On Artemis I, the heat shield performed unexpectedly, more charring than predicted. Engineers spent months analyzing, testing, certifying it for crew. Now it's ready. When Orion returns to Earth at 32 times the speed of sound, the heat shield will face temperatures of 2,760 degrees Celsius, half as hot as the surface of the sun. If it fails, the crew doesn't come home. It's the most critical piece of hardware on the spacecraft, and on top of everything sits the launch abort system. If something goes wrong during launch, if the rocket starts to fail, this system fires, pulling Orion and its crew away from danger in milliseconds. It's been tested successfully. It's ready, and hopefully, it will never be used. Flight Day 1, Launch Day. The crew straps in hours before dawn. The countdown ticks down. 10, 9, 8. The engines ignite, but the rocket holds, computers checking everything is perfect. Then the hold downs release, and 8.8 million pounds of thrust push them skyward. In 2 minutes, they're through the atmosphere. In 8, they're in space. For the first time in 50 years, humans are on their way to the moon. Once in orbit, the crew has work to do. They'll spend about 24 hours circling Earth checking every system, life support, communications, navigation. If anything's wrong, they can turn around and come home. but everything checks out. Their go for the moon. One of the first tasks is a proximity operations demonstration. The upper stage, now empty, becomes a target. Victor Glover takes manual control of Orion and flies toward it, carefully, precisely, then backs away. It's practice for future missions, when Orion will need to dock with landers and space stations. In the blackness of space, with Earth below, the crew proves they can fly this machine. Flight Day 2. The critical moment. Translunar injection. The upper stage fires for about 5 minutes, pushing Orion from Earth orbit to lunar trajectory. When the burn is complete, they're committed. There's no turning back now. Earth shrinks in the window behind them. Ahead, the moon. For the next 3 days, they cruise. The routine is simple. Check systems, eat, exercise, sleep. They send video messages home, each one taking longer to arrive as the distance grows. Earth shrinks from a world to a sphere to a dot. Ahead, the moon swells in the window. By Flight Day 5, they cross into the lunar sphere of influence, where the moon's gravity pulls harder than Earth's. They're no longer Earth's children, they belong to the moon now. Flight Day 6, the moment they've trained for. Orion swings behind the moon, and Earth disappears. Communication cuts out. For 30 to 50 minutes, they're alone, the first humans ever to lose contact with Earth while so far from home. And then they look out the window. The far side of the moon, ancient highlands, basins carved by impacts billions of years old. No human has ever seen this with their own eyes. Christina Koch grabs the camera. Jeremy Hansen starts describing what he sees, the colors, the textures, the shapes. For 3 hours they observe, photograph, record. They're scientists now, explorers, doing what humans do best, seeing, learning, understanding. At closest approach, they're about 7,500 kilometers from the lunar surface, farther than Apollo, but close enough to see details no human has ever seen. The moon fills the window, a basketball at arm's length. They're moving at 36,000 kilometers per hour. In the silence of the far side, with no radio, no Earth, no one but themselves, they are the most isolated humans in history. When they emerge from behind the moon, Earth reappears, a tiny blue dot, but growing. They're on a free return trajectory. The moon's gravity has flung them back toward home like a slingshot. No engines needed now, just patience. For 3 days, they watch Earth grow from a dot to a sphere to a world. Home is calling them back. Flight Day 10, re-entry. The service module separates, burning up in the atmosphere as planned. The heat shield faces forward as Orion hits the atmosphere at 40,000 kilometers per hour. Plasma builds around the capsule. Temperatures reach 2,060 degrees. Communications blackout. 7 minutes of silence. Inside, the crew is pushed back into their seats by 6 times Earth's gravity. They can barely breathe, barely move, but the heat shield holds. The parachutes deploy. First the drogues, then the mains, and then splashdown. The Pacific Ocean, off the coast of San Diego. After 10 days and 2 million kilometers, Orion splashes down. The capsule bobs gently in the waves. Recovery divers approach in boats. The hatch opens and the crew emerges, tired, dehydrated, but alive. They've done it. They've gone to the moon and back. For the first time in 50 years, humans have left Earth orbit and returned safely. The door to the solar system is open again. But not everything has gone smoothly. On Artemis the Fern, the heat shield performed unexpectedly, more charring than predicted. Engineers spent months investigating, running tests, building models. They ultimately certified it for crew, but some in the space community remain concerned. The crew knows the risk. They've trained for it. They trust the engineers. But the question lingers. Will it hold? In February 2026, just weeks before launch, a problem emerged. Helium flow to the upper stage was interrupted. The rocket might need to roll back to the vehicle assembly building for repairs. The March 6 launch date suddenly seemed uncertain. This is the reality of spaceflight. Problems arise, schedules slip, and the crew waits. They train, they prepare, they stay ready. But the rocket decides when it's ready to fly. Beyond Earth's magnetic field, radiation is a constant threat. Cosmic rays from distant supernova, solar particles from our own sun. Orion has a radiation shelter, a small space with extra shielding where the crew can wait out a solar storm. But they'll still be exposed to levels far higher than on the space station. Cancer risk increases. DNA damage accumulates. It's the price of exploration. And then there's the isolation. No one can rescue them if something goes wrong. No spacecraft can reach them in time. They're on their own, 250,000 miles from home, with only each other and the systems they trust. It takes a special kind of person to accept that, to strap into a capsule, watch Earth shrink to a dot, and keep going anyway. The crew of Artemis II are those people. Artemis II isn't just a test flight, it's a science mission. The crew will spend hours observing the moon, documenting features that have never been seen by human eyes. They'll take thousands of photos, record detailed descriptions, and bring back data that will keep scientists busy for years. From their vantage point, the crew can see details that satellites miss. They'll focus on the Oriental Basin, a massive impact crater on the western edge of the moon. They'll study ancient lava flows, impact melt, the difference between the near side and the far side. And they'll do it with the most powerful scientific instrument ever invented, the human eye. The crew are also research subjects. They'll wear monitors to track radiation exposure. They'll perform cognitive tests to see how deep space affects the brain. They'll provide blood and urine samples to study how the body responds to the deep space environment. Every piece of data helps prepare for Mars, for longer missions, farther from home. During the mission, Orion will deploy several small satellites, CubeSats, that will study the moon and test new technologies. Some will look for water ice, others will test navigation systems. Each one is a stepping stone to something bigger, a proof of concept for future exploration. Why does this matter? In a world full of problems, climate change, conflict, division, why spend billions to send 4 people to the moon? Because exploration is what we do. It's who we are. When we look up at the night sky, we wonder. We dream. We imagine what's out there. And then we go. Not because it's easy, but because it's hard. Because the challenge makes us better. Because the journey teaches us something about ourselves. Reed Wiseman says they're doing this for everyone back on Earth. Victor Glover thinks of the children who will watch and dream. Christina Koch remembers the girls who never saw themselves in space, until now. Jeremy Hansen carries the hopes of a nation, and of all nations. 4 humans, 1 mission, representing all of us. 50 years ago, we left. We said we'd return, and then we didn't. The years passed, the astronauts aged, the memories faded, but the dream never died. And now finally we're going back. Not just to visit, but to stay. Not just for ourselves, but for everyone who ever looked up and wondered. Artemis II is the first step, the next giant leap, and it starts now. Thank you for watching. If this journey inspired you, share it with someone who needs to dream. Comment below. What does the return to the moon mean to you?
गार्नियर कलर नेचुरल अब चले 2 महीने सिर्फ 199 रुपए के साशे पैक में।
We humans like to think we understand scale. We know the Empire State Building is tall. We know Mount Everest is massive. We know Earth is vast. But the universe has a way of humbling us. Every time we think we've found the biggest, the cosmos reveals something larger. Today, we journey to the current record holder, the largest known galaxy in the universe. Its name is IC 1101. It contains 100 trillion stars. It spans 6 million light-years, and at its heart lurks a black hole weighing 40 billion suns. This is the story of the cosmic titan that defines big. Before we dive in, we need to understand what largest means. Is it the widest? The most massive? For IC 1101, the answer is all of the above. It is the undisputed heavyweight champion of the cosmos. Estimates place its diameter between 3 and 6 million light-years, 50 to 60 times larger than the Milky Way. In this documentary, we'll explore every aspect of this cosmic titan, from its discovery in 1790 to the latest observations. The story begins on June 19, 1790. German-British astronomer William Herschel was sweeping the skies. A century later, it was included in the Index catalog and given the designation IC 1101. In the 1920s and 30s, Edwin Hubble proved that these nebulae were actually separate island universes. Over the following decades, IC 1101 became the subject of intense study, from radio waves to X-rays. Let's look at the official measurements. IC 1101 has a diameter that is already 4 to 5 times larger than our Milky Way. But the galaxy's diffuse stellar halo extends much further, out to a radius of about 2 million light-years. When you include the intra-cluster light, the total extent may reach an astonishing 6 million light-years in diameter. Now we come to the most staggering number: stars. IC 1101 contains an estimated 100 trillion stars. Let me repeat that: 100 trillion suns.
To put that in perspective, the Milky Way contains about 100 to 400 billion stars. IC 1101 has more than 1,000 times as many stars as our galaxy. It is a scale that defies human comprehension. If you tried to count them at 1 per second, it would take you 3 million years. 100 trillion stars. These aren't just any stars. Most of them are ancient. Some are more than 7 billion years older than the Sun. They formed early in the universe's history. This is not a place of new star formation. It's an archive of time. In the core of IC 1101, stars are packed 1,000 times denser than in our neighborhood. It is an eternal blaze. There would be no true night, no darkness, just an eternal blaze of starlight. The nearest stars are light days away. Surrounding the main body is a vast stellar halo, a diffuse sphere of stars extending millions of light years. These stars were stripped from smaller galaxies over billions of years. They orbit in the darkness, barely detectable. Does IC 1101 have planets? Moons? The answer is almost certainly yes. With 100 trillion stars, the numbers are staggering. Even if only 1% of stars have planets, IC 1101 would contain 1 trillion planetary systems. Think of the possibilities. The core of IC 1101 might be one of the most dangerous places for life. Gravitational interactions would be constant, supernovae would be frequent, radiation levels would be intense. Any life there would have to be incredibly resilient. But not all of IC 1101 is chaotic. The outer halo is much quieter. Stars there are spaced further apart. There could be billions of such stars, each with its own planets, its own moons, and its own potential for life. If planets exist, moons exist. In IC 1101, the number of moons would be truly astronomical. Billions of worlds. There could be billions of such moons, worlds where life might have a chance in the hidden depths of icy oceans.
At the very center of IC 1101 lies something even more extraordinary. In 2017, astronomers made a remarkable discovery.
IC 1101 has the largest galactic core of any galaxy known. The core radius is about 13,700 light-years. That is more than 4 times larger than the core of A2261-BCG, another giant elliptical galaxy, and an order of magnitude larger than the cores of other massive ellipticals. This diffuse core suggests a violent history, as Dulo et al. Noted in 2017. This is a remarkably large depleted core in the Able 2029 BCG IC 1101. What created this enormous core? Most likely, the supermassive black hole at the galaxy's center. Estimates of IC 1101's central black hole range from 40 to 100 billion times the mass of our Sun. That's one of the most massive black holes ever discovered. An ultramassive black hole near the upper bound of cosmological limits. For comparison, the black hole at the center of our Milky Way, Sagittarius A, is only 4 million solar masses. IC 1101's black hole is more than 10,000 to 25,000 times more massive. It is truly a cosmic giant. Universe Today confirms this estimate of 40 to 100 billion solar masses for the central black hole. To visualize, this event horizon would swallow our entire solar system many times over. How does a black hole get this massive? The leading theory involves repeated galaxy mergers over cosmic time. IC 1101 has cannibalized hundreds, perhaps thousands of smaller galaxies over its 13 billion year history. Each time 2 galaxies merge, their central black holes eventually merge as well, creating ever larger giants. The gravitational slingshots from these mergers also fling stars out of the central region. This creates the large diffuse core we observe today, nearly empty of its original star population. This process, called core scouring, explains why IC 1101's center is so empty of stars. IC 1101 has a very bright radio source at its center, associated with its active galactic nucleus. Observations from the NRAO VLA Sky Survey have detected intense radio emissions near the core. This is consistent with an active black hole accreting matter from its surroundings. The galaxy is still active, still growing, and still consuming everything in its path. As reported by the NRAO, a very bright radio source has been detected at the heart of this giant. IC 1101 isn't the only giant in the universe, but it remains the undisputed record holder. Let's compare it to other cosmic behemoths to see how they measure up against the king. A2261 BCG has a similarly large core, about 10,000 light-years across, but its overall size is smaller. Phoenix A has a central black hole estimated at 100 billion solar masses, rivaling IC 1101. However, The host galaxy of Phoenix A is smaller than the vast expanse of IC 1101. NGC 4889 has a black hole of about 21 billion solar masses and a diameter of 300,000 light-years. While massive, it is still dwarfed by the sheer scale of IC 1101. Scientific sources confirm. IC 1101's core radius remains the largest ever measured. By every metric, IC 1101 comes out on top as the heavyweight champion of the cosmos. It has the largest diameter, over 60 times that of our own Milky Way galaxy. It contains 100 trillion stars, 100 times more than Andromeda, and its black hole is an order of magnitude larger than even the famous M87. It is the complete package, the undisputed king of the observable universe, a true cosmic titan, standing as a testament to the violent and grand history of our universe. Thank you for watching this cosmic journey. Don't forget to subscribe for more space exploration. IC 1101 doesn't exist in isolation. It's the central dominant galaxy of the Abell 2029 galaxy cluster, one of the richest galaxy clusters known. This cluster contains thousands of individual galaxies. All are bound together by gravity and orbiting around the central titan. The cluster's total mass, including dark matter, is estimated at about 100 trillion solar masses. Abell 2029 is a massive galaxy cluster containing thousands of galaxies and vast amounts of hot gas and dark matter. IC 1101 stands as the undisputed king of this massive gravitational empire. The space between galaxies in Abell 2029 is not empty. It's filled with a hot, diffuse plasma. At temperatures of tens of millions of degrees, it glows brightly in X-rays. This intracluster medium is held in place by the cluster's immense gravitational field. IC 1101 sits at the very center of this hot gas, accreting material and growing still. The intracluster medium in Abell 2029 reaches temperatures of 30 million degrees, a hellish environment where even atoms are stripped of their electrons by intense heat. The dynamics of Abell 2029 are fascinating. IC 1101's major axis is perfectly aligned. It aligns with the direction from which the cluster accretes matter from its neighbor, Abell 2033. This alignment suggests that the galaxy's structure has been shaped by the cosmic flow. IC 1101 literally points toward its primary source of growth. The alignment indicates that IC 1101's structure has been shaped by the accretion of material from Abell 2033, a testament to the violent and orderly history of our universe's largest structures. How does a galaxy become this large? Through a process called hierarchical merging. Over the 13.8 billion years since the Big Bang, IC 1101 has grown. It has cannibalized hundreds, if not thousands, of smaller galaxies that fell into the cluster. Each merger added more stars, more gas, and more dark matter to the growing behemoth. IC 1101 owes its size to many collisions of galaxies, about the size of the Milky Way and Andromeda. It is a monster built from the remains of countless cosmic ancestors. The enormous, diffuse core of IC 1101 is a direct result of this merger history. These black hole mergers act like cosmic slingshots, flinging stars out of the center. Over billions of years, this process leaves a large, relatively empty region at the galaxy's center. The stellar mass deficit is about 490 billion solar masses, 500 billion stars ejected. Core scouring by binary black holes likely created this massive, depleted core. With a core radius of 13,700 light-years, it is a hollow giant. Unlike spiral galaxies like our Milky Way, IC 1101's star formation ceased billions of years ago. There is no evidence of dust lanes, no signs of recent star formation, and no nuclear emission. The galaxy is essentially a fossil, a collection of ancient stars that formed early in history. These stars have been aging ever since. It grows only by cannibalizing, not by creating. IC 1101 is a red and dead galaxy. No new stars have formed in billions of years. It survives now as a celestial predator, adding to its mass one neighbor at a time. IC 1101's story isn't over. Even now it continues to grow. Galaxies in the Abell 2029 cluster are slowly falling toward the center, destined to be consumed. Over the next billions of years, IC 1101 will continue to accrete more mass and more stars. It may eventually reach 200 trillion stars, or even more. There's no known upper limit. As long as there's matter to consume, it will keep growing. IC1101 will continue to grow by consuming neighboring galaxies for billions of years to come. In the incredibly distant future, trillions of years from now, even galaxies like IC1101 will die. In 10 to the power of 100 years, the universe will be a very different place. Stars will burn out. Black holes will evaporate. The galaxy will slowly fade. Its 100 trillion stars will wink out over trillions of years. The ultimate fate of all galaxies is to fade into darkness, but that day is trillions of years away. For now, and for billions of years to come, IC1101 will remain the largest known galaxy in the universe.
IC1101 is a galaxy of superlatives. It is the largest known galaxy in the universe, spanning 6 million light-years and containing 100 trillion stars. It has the largest known galactic core, one of the most massive black holes ever discovered, and a dark matter halo that holds an entire cluster together. It is ancient, golden, and fossilized, a window into the early universe when galaxies were still forming and growing. IC1101 is the largest galaxy we know of, and it's not even close. Studying IC1101 teaches us about the extremes of galaxy formation. It shows us what happens when galaxies merge over and over again for billions of years. It reveals the relationship between supermassive black holes and their host galaxies. It demonstrates the role of dark matter in holding clusters together. And it reminds us that the universe is capable of creating structures far beyond anything we could have imagined. IC1101 pushes the limits of what a galaxy can be, and yet, for all its staggering size, IC1101 is just one galaxy among billions. The universe contains countless other behemoths, each with its own story, its own history, its own mysteries. IC1101 may be the largest we've found so far, but who knows what else is waiting to be discovered? The cosmos is vast beyond imagining, and we've only just begun to explore it. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself.
We spend our lives thinking we matter, that our problems are important, that our existence is significant. But the universe has a different perspective. It doesn't care about our wars, our loves, our dreams. It doesn't even notice us. This is the disturbing truth about our size in the universe. It's a truth we avoid, but it's a truth we need to face. How big are we? Not individually, not as a species, but as a presence in the cosmos. When you look at the numbers, the answer is unsettling. We are not just small, we are almost nothing. And that realization, if you let it sink in, can change everything. In this documentary, we will take a journey. We'll start at the human scale, the scale we know best, and zoom out. We'll travel past the moon, past Mars, past the sun. We'll leave our solar system, our galaxy, our supercluster. We'll reach the edge of what we can see. And when we get there, we'll ask the question that everyone avoids. What are we, really? We begin here with a human, about 1.8 meters tall, about 70 kilograms. This is the scale we know. This is the scale we measure everything else by. From here, we will expand. At 10 kilometers, we see a city, millions of people, millions of stories. This is the scale of our daily lives. This is the scale we think is big. At 1,000 kilometers, we see a continent. Entire nations fit within this view. Civilizations have risen and fallen here. At 10,000 kilometers, we see the whole Earth, 12,042 kilometers in diameter. Every human who ever lived, every city ever built, all on this sphere. This is our home. This is everything we know. And it is about to become very, very small. The first blow to our ego, the sun. You could fit 1.3 million Earths inside it. It contains 99.8% of all the mass in our solar system. We are not the center. We are not even a significant part. We are a speck orbiting a speck. The solar system is mostly empty space. At the speed of light, it takes 8 minutes to reach Earth from the Sun, 5 hours to reach Pluto. Our fastest spacecraft, Voyager 1, took 35 years to leave the solar system. It's been flying since 1977. It's now 15.5 billion miles away. That's 0.026 light years. The nearest star is 424 light years away. We haven't even left our driveway. Let's put it in perspective. If the Sun were the size of a basketball, Earth would be a peppercorn 26 meters away. Pluto would be a grain of sand a kilometer away. And the nearest star, Proxima Centauri, would be another basketball 7,000 kilometers away. That's the distance from New York to Los Angeles. In between, nothing, just empty space. This is our cosmic address, a tiny home in an impossibly large neighborhood. Beyond our driveway lies a neighborhood so vast that light itself takes years to cross it. A silence that defines our existence. Every star we see is another sun, another potential home, yet separated by gulfs of nothingness we can barely comprehend. We have sent our eyes and our voices into the dark, but we remain tethered to our small blue dot. Some questions seem too big to answer. We answer them anyway, because knowing our place is the first step to finding our way. From the sun's fire to the cold edge of the void, this is our cosmic address, small, fragile, and utterly unique. Join us as we continue our journey through the impossible. Subscribe and explore the cosmos with us. Some questions seem too big to answer. We answer them anyway. Our solar system is far larger than you've been told. The solar system doesn't end at Pluto. To find its true boundary, we have to look much, much further out. Beyond the Kuiper Belt lies the Oort cloud, a gargantuan sphere of icy comets stretching across the void. It extends a quarter of the way to the nearest star. This is the true edge of our solar system, and it's still just our backyard. To grasp the scale of what lies beyond, we need a new ruler, a way to measure the unimaginable distances between stars. To measure the space between stars, we use light years, the distance light travels in 1 year. Light is the fastest thing in the universe, yet, even at its incredible speed, the distances remain daunting. 1 light year is 9.46 trillion kilometers. That's the scale we're about to enter as we leave home behind. Our entire world, our entire history, becomes a single pixel in the darkness. We are heading toward our neighbor, Proxima Centauri, the nearest star to our sun, a faint red dwarf glowing dimly in the stellar neighborhood. It is 424 light years away, a distance so vast it defies our primitive human intuition. At our current technology, it would take 70,000 years to get there. That's longer than human civilization has existed. Think of every empire, every invention, and every war. All of it occurred in a fraction of that travel time. And remember, this is the closest star, the very closest, in a galaxy of hundreds of billions. Our solar system is a speck. Our stellar neighborhood is a speck. We are a speck within a speck. Between us and the rest of the universe lies an ocean of silence, a void that reminds us of our own insignificance. But to understand where we are going, we must first accept how small we really are. The Alpha Centauri system is just the beginning of a journey that spans the entire cosmos. From here, the distances only grow. The numbers become so large they lose all meaning. Yet, here we are, on our tiny pale blue dot, looking out and asking, what else is there? We are travelers on a journey through the infinite, and the next chapter is about to begin. Some questions seem too big to answer, but we're going to keep looking, because the speck matters.
Our solar system is inside a bubble of hot, thin gas called the local bubble. It's about 1,000 light years across. Inside it are about a dozen stars. The nearest ones are tens of trillions of kilometers away. This is what space is, not stars, not planets, empty. Vast, cold, silent emptiness. The stars are islands in an ocean of nothing. And we are on one of those islands. Beyond our sun's reach lies Proxima Centauri, a small red dwarf. Only 4.2 light years away, yet an unreachable distance for now. It is the closest neighbor we have in this cosmic void. Proxima orbits a binary pair, Alpha Centauri A and B, 2 brilliant suns similar to our own, dancing in the darkness. A triple star system that serves as our first galactic milestone. To cross this gap at light speed would take over 4 years. For our fastest probes, it is a journey of 70 millennia. Space is not just big, it is fundamentally disconnected. This void is not truly empty. It is filled with the interstellar medium, the breath of dying stars and the seeds of new ones. We are passing through a patch called the local interstellar cloud. Before we reach the void, we must pass through the Oort cloud.
1 trillion icy wanderers marking the graveyard of our solar system's birth. This is the final frontier before the true interstellar deep. Our sun is a traveler, moving through this bubble for 5 million years. A fleeting moment in galactic time, an accidental visitor in this void. Soon, we will leave the bubble behind, heading into the unknown. The void between stars defines us as much as the stars themselves. Solitary beacons in a dark, infinite ocean. Some questions seem too big to answer. We answer them anyway.
The universe is a vast expanse of mystery, but none so close as the home we call our own. To understand our place, we must first look at the grand architecture of the Milky Way. This is our galaxy, the Milky Way. At 100 light-years, the stars begin to cluster. 1,000 light-years out, the great spiral arms start to emerge from the darkness. 10,000 light-years, the galactic center glows with the light of billions. 100,000 light-years across, a colossal structure containing 100 to 400 billion stars. Our sun is just one of them, an ordinary star in an ordinary arm of an ordinary galaxy. But ordinary does not mean insignificant. It just means we are part of something much, much larger. We are not at the center of our galaxy, not even close. We're 27,000 light-years from the center, tucked away in a quiet corner, in a minor spiral arm called the Orion Arm. Not special, not central, just another star. When you look up at the night sky, everything you see feels infinite, but it's an illusion. Every star you can see with your naked eye is within just 1,000 light-years of Earth. That's only 1% of the diameter of our galaxy, a tiny fraction of the whole. The rest of the galaxy, 99% of it, is invisible to us without the aid of telescopes. Hidden behind clouds of gas and dust, billions of worlds remain unseen. At the very heart of this vast structure lies a monster, a supermassive black hole. With a mass of 4 million suns, it holds the entire galaxy in a gravitational embrace. But stars and black holes are only part of the story. There is an invisible skeleton here. Dark matter. It outweighs all the stars and planets 10 to 1. Silent, invisible, essential. Our galaxy is not alone. It's part of a small family known as the Local Group. In 4 billion years, we will collide with our neighbor, Andromeda, to form a new, giant home. In this vastness, our smallness is not a tragedy. It's a perspective. A reminder that we are part of a grand, spinning masterpiece of light and gravity. This is our home, a tiny dot in a sea of stars. Join us as we continue to explore the impossible.
The Milky Way is not alone. It's part of the Local Group, 54 galaxies bound together by gravity. The largest is Andromeda, 2.5 million light-years away. It's heading toward us. In 4.5 billion years, we will collide. This massive merger will create a new, giant elliptical galaxy. This group spans 10 million light-years, a small family in a much larger cosmic neighborhood. We have smaller companions too, the Magellanic Clouds. They're visible from the southern hemisphere. They've been our neighbors for billions of years, but their proximity comes at a cost. They're slowly being torn apart by our galaxy's gravity, eventually becoming part of our own. The Local Group is just a small part of the Virgo cluster, a swarm of over 1,300 galaxies. At its center is M87, a giant elliptical galaxy with a black hole 6.5 billion times the mass of our sun. This cluster is the heart of our local cosmic city, exerting a massive gravitational pull on everything around it. The Virgo cluster is part of the Virgo supercluster, thousands of galaxies spanning 110 million light-years. Our Local Group is just a tiny suburb in this vast cosmic city, barely a footnote in the grand scale. But even this city of cities has a mysterious force guiding its motion. There's something strange about the Virgo supercluster. Everything is flowing toward a point called the Great Attractor. We can't see it, it's hidden behind our galaxy, but its gravity is pulling us. Something massive is out there. We don't know what it is. It's a mystery that reminds us how much of the universe remains in the shadows. The Virgo supercluster is part of an even larger structure called Laniakea, immeasurable heaven in Hawaiian. It spans 520 million light-years. It contains 100,000 galaxies. Our Local Group is a speck within it. The largest structure in the universe is the cosmic web. Filaments of galaxies stretching across billions of light-years, separated by voids where almost nothing exists. This is the architecture of everything, and we are a speck in a speck in a speck. This is everything we can see. The observable universe, 93 billion light-years across,
2 trillion galaxies. Each galaxy has billions of stars. Each star may have planets. The numbers are so vast that they lose meaning. In 2004, astronomers pointed Hubble at a tiny patch of sky, the size of a grain of sand held at arm's length. The observable universe is not the whole universe. It's just the part we can see. The light from beyond hasn't had time to reach us, and it may never reach us because the universe is expanding faster than light can travel. If cosmic inflation happened, and the evidence suggests it did, then the entire universe is at least 10 to the 23rd times larger than the observable universe. That's a 1 followed by 23 zeros. At that scale, our observable universe is a single atom in a body the size of the observable universe. We are not just small, we are smaller than we can imagine. Some theories go further. Inflation might be eternal, happening forever in different regions. If that's true, then our universe is just one bubble in an infinite sea of bubble universes, each with its own physical laws, each potentially infinite, and we are in one of them. Let's add it up. A human is 1.8 meters tall. Earth is 12,742 kilometers across. The solar system is 1.5 light-years across. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years across, and the unobservable universe may be 10 to the 23rd times larger. We are not just small, we are not just insignificant, we are almost nothing. If the entire universe were the size of a grain of sand, the Milky Way would be a speck of dust on that grain. The Earth would be a subatomic particle. You would be smaller than an atom. And that's if the universe is finite. If it's infinite, then we are literally nothing. This is the disturbing truth. In the grand scale of the cosmos, we are not even a pixel. Every human who ever lived, every war, every love, every dream, all of it on a mote of dust suspended in a sunbeam. The universe doesn't know we're here, it doesn't care, and it never will. But here's the thing, size doesn't matter. Significance isn't measured in light years. It's measured in awareness, in consciousness, in the ability to look at the cosmos and ask, what am I? Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. We are small, smaller than small. In the cosmic scale, we are less than a pixel, but we are the part of the universe that can see itself. We are the part that can wonder. We are the part that can ask. That is not nothing, that is everything. We are small, infinitely small, but we are significant because we are aware, because we can look at the universe and understand it, just a little. Because we can ask questions, because we can wonder. The universe is vast beyond imagination, but we are the part of it that can say, I am here. And that is everything. Thank you for joining us on this journey through scale. If it changed your perspective, share it with someone who needs to be reminded how big the universe is and how small we are. Comment below, at what point in this journey did you feel the most disturbed?
This is Alaknanda, a massive grand design spiral galaxy located 12 billion light-years from Earth. At first glance, it looks ordinary, beautiful but ordinary. But here's what makes it extraordinary. We're seeing it as it existed just 1.5 billion years after the Big Bang. According to everything astronomers thought they knew, this galaxy should not exist. In the early universe, galaxies were supposed to be messy, chaotic, clumpy collections of gas and stars still finding their shape. But Alaknanda looks like it belongs in the modern universe, alongside galaxies billions of years older. It has 2 sweeping spiral arms wrapped around a bright, round, central region. It's organized, it's mature, and it's breaking all the rules. In late 2025, two astronomers from the National Center for Radio Astrophysics in Pune, India, Rashi Jain and Yogesh Wadadekar, were studying images from the James Webb Space Telescope. They were examining data from 21 different filters, dissecting light from the early universe. And then they found something that made them stop. A galaxy so perfectly formed, so unexpectedly mature, that it challenged everything they thought they knew about cosmic history. Rashi Jain and Yogesh Wadadekar spend their days studying the cosmos from Pune, India. Using the most powerful space telescope ever built, the James Webb Space Telescope, they were peering back in time, hoping to understand how galaxies formed in the universe's infancy. What they found would make headlines around the world. The James Webb Space Telescope is uniquely powerful. Its infrared vision allows it to see through cosmic dust and look further back in time than any telescope before. For their study, Jain and Wadadekar used 21 different filters, each one capturing a different wavelength of light. Together, these images would reveal the true nature of a galaxy from the dawn of time. They named it Alaknanda, after the Himalayan river that serves as one of the headstreams of the sacred Ganga. Why this name? Because the Alaknanda River is the sister of the Mandakini, and Mandakini is the Hindi name for our own Milky Way galaxy. Just as the rivers are connected in the mountains, this distant spiral is connected to our cosmic home. A poetic name for a poetic discovery. Alaknanda lies at a redshift of about 4, meaning its light has been traveling for more than 12 billion years to reach us. We are seeing this galaxy as it appeared just 1.5 billion years after the Big Bang. The universe was only 10% of its current age, and yet here was a galaxy that looked remarkably similar to our own Milky Way, which is 10 billion years older.
Alaknanda is not a small galaxy. It spans about 32,500 light-years across, roughly 1/3 the size of the Milky Way. For a galaxy that existed when the universe was in its infancy, this is enormous. Most galaxies from this era were small, irregular, and still forming. Alaknanda was already grown up. The galaxy contains roughly 10 billion times the mass of our sun and stars. That's 10 billion stars. Already formed, already organized into a beautiful spiral structure. To have assembled this many stars in just 1.5 billion years is astonishing. The universe simply hadn't been around long enough, or so we thought. And Alaknanda isn't done growing. It's forming new stars at a staggering rate, about 63 times the mass of our sun every single year. Compare that to the Milky Way, which forms just 1 to 2 solar masses annually. Alaknanda was in a cosmic growth spurt, churning out stars 30 to 60 times faster than our own galaxy. Here's the puzzle. Analysis suggests that half of Alaknanda's stars formed after the universe was about 1.3 billion years old, meaning it built 5 billion solar masses of stars in just 200 million years. That's extraordinarily fast by cosmic standards. Somehow, this galaxy pulled together enormous amounts of gas and organized it into a beautiful spiral disk in an astronomically short time. To understand why Alaknanda is so surprising, we need to understand what astronomers expected to find. The traditional model said early galaxies would be chaotic, clumpy, turbulent, disordered. Gas clouds would collapse in bursts, creating galaxies too hot and unstable to form a calm, rotating disk. But Alaknanda tells a different story. Its structure is not chaotic, it's organized. Using a tool called GalFit, which models galaxies based on their light profiles, researchers confirmed it has 2 symmetric spiral arms, a well-formed disk, and a bright central bulge. It has the structural maturity of a galaxy billions of years older. Lead author Rashi Jain put it this way: finding such a well-organized spiral disk at this epoch tells us that the physical processes driving galaxy formation, gas accretion, disk settling, can operate far more efficiently than current models predict. It's forcing us to rethink our theoretical framework. Alaknanda is not alone. Webb has found other galaxies that are too mature, too early. But Alaknanda is one of the clearest examples of a grand design spiral from the universe's infancy. It's forcing astronomers to go back to the drawing board. So how did it form its beautiful spiral arms so quickly? Astronomers have a few ideas. First possibility, interaction. Researchers noticed a small spheroid galaxy nearby, a possible companion. When galaxies pass close, gravity can trigger spiral arms. The problem? Arms formed this way usually fade quickly. Alaknanda's arms are clear, prominent, and permanent looking. Second possibility, clump dissolution. Early galaxies were often clumpy regions of intense star formation. As these clumps dissolve over time, they might redistribute gas into spiral patterns faster than we thought. Alaknanda could have evolved from a clumpy mess into this beautiful organized state in record time. To find the real answer, we need more data. Astronomers plan to use ALMA, the Atacama Large Millimeter-Submillimeter Array in Chile. By measuring how fast Alaknanda is rotating and whether its disk is cold and orderly or hot and turbulent, they can finally determine which story is true. Alaknanda is more than just a beautiful discovery. It's a sign that our understanding of the early universe needs to evolve. Galaxy formation models will have to address how such large, luminous, and organized galaxies could exist so early in cosmic history. The early universe was not the simple, chaotic place we imagine. This is the James Webb Space Telescope revolution. Since it began operations, Webb has repeatedly surprised us finding fully formed galaxies earlier than expected, black holes that grew too fast, and now, a grand design spiral from the universe's infancy. Each discovery forces us to ask new questions. On Earth, the Alaknanda River has flowed for millennia, carving valleys, sustaining life. In space, the Alaknanda galaxy has spun for billions of years, creating stars, building worlds. Both are named for the same thing, the eternal flow of existence, the beauty of creation. Two astronomers in Pune, India, looked at data from a telescope orbiting 1 million miles from Earth. They saw light that had traveled for 12 billion years. And in that ancient light, they found a galaxy that challenges everything we know. This is what discovery looks like. This is what it means to be human. Alaknanda is one galaxy among billions. But it tells us something profound. The universe is richer, stranger, and more wonderful than we ever imagined. As new telescopes come online, we will keep discovering and keep being surprised. Because the cosmos never stops teaching us, we just have to keep looking up.
In the vast darkness of the universe, beyond the reach of ordinary light, there exists something so powerful that it bends the very fabric of reality. A force born from dying stars, a region where gravity dominates everything. This is the story of black holes, the most mysterious objects ever discovered in space. Black holes are not born in darkness. They begin their lives as massive stars, giants that burn hotter and brighter than our sun. For millions of years, nuclear fusion holds them together. But when their fuel runs out, gravity wins. And when gravity wins, the universe witnesses one of its most violent events. When a massive star collapses under its own gravity, it explodes in a supernova, an event so bright it can outshine entire galaxies. But at the heart of that explosion, something extraordinary happens. The core compresses into an infinitely small point, creating a gravitational monster. This is a black hole, not a hole in space, but a region where gravity becomes unstoppable. At its center lies a singularity, a point of unimaginable density. Surrounding it is the event horizon, the boundary beyond which nothing, not even light, can escape. The boundary surrounding a black hole is called the event horizon, the point of no return. Once anything crosses this invisible line, escape becomes impossible. Gravity becomes so intense that even light cannot break free. Beyond this boundary, the laws of physics begin to collapse. Black holes do not just consume matter, they bend space and time itself. As light passes near them, it curves, creating distorted images of distant stars and galaxies. This effect, known as gravitational lensing, proves that black holes are not science fiction. They are real cosmic architects. There are different types of black holes. Stellar black holes form from dying massive stars and are only a few times heavier than our sun. But supermassive black holes are giants, millions or even billions of times more massive, hiding at the centers of galaxies. At the center of almost every galaxy lies a supermassive black hole, including our own Milky Way. Though invisible, its gravitational pull controls the motion of billions of stars. It acts as the hidden anchor of the galaxy, shaping its structure over cosmic time. Our galaxy's supermassive black hole is called Sagittarius A star. It is about 4 million times more massive than our sun. Stars orbit around it at incredible speeds, revealing its presence. Though silent and dark, its influence dominates the galactic core. If a star ventures too close, it faces a terrifying fate. The intense gravity stretches it like spaghetti, a process scientists call spaghettification. Tidal forces tear the star apart, forming streams of hot plasma that spiral into the black hole. According to Einstein's theory of general relativity, gravity is not simply a force, it is the bending of space and time. A black hole creates the deepest curve possible. The deeper the curve, the stronger the gravity. Near a black hole, time itself slows down. If you could observe a black hole safely from a distance, you would witness something extraordinary. Time near the event horizon moves slower compared to distant space. For someone falling in, time would appear normal, but to an outside observer, they would seem frozen in time. Before there was anything, no stars, no galaxies, no planets, no life, there was nothing. Not empty space, not darkness, not even time itself. And then, in a fraction of a second, everything changed. From a single point smaller than an atom, all the matter, all the energy, all the space and time that would ever exist erupted into being. This was the Big Bang, the most important event in the history of everything. And this is its story. The Big Bang wasn't an explosion in space. It was an explosion of space itself. Every point in the universe was once compressed into an infinitely hot, infinitely dense singularity. Then, for reasons we're still trying to understand, it expanded. Rapidly, violently, and that expansion continues to this very moment. The galaxies aren't flying through space. They're flying with space, carried along by the momentum of that first incredible instant. Why does the Big Bang matter? Because it's our origin story. Every atom in your body, the carbon in your cells, the oxygen in your lungs, the iron in your blood, was forged in stars that lived and died billions of years ago. And those stars themselves were born from the aftermath of the Big Bang. When you look up at the night sky, you're not just seeing distant suns, you're seeing your own past. You're seeing where you came from. We are, all of us, children of the Big Bang. In this documentary, we'll travel back in time to the very beginning. We'll witness the first picosecond, when the laws of physics were forged. We'll watch as matter triumphs over antimatter, as the first atoms form, as stars ignite and galaxies take shape. We'll follow the cosmic story all the way to the present day. To you, watching this video, asking the same questions humans have always asked. Where did we come from? How did it all begin? The answers are written in the light from the edge of the universe. Let's go find them. For most of human history, we assumed the universe had always been here, eternal, unchanging. The steady-state theory was the accepted wisdom. Even Einstein added a cosmological constant to force the universe to remain static. In the 1920s, Edwin Hubble made a discovery that would shatter the steady-state universe. He noticed something strange. Light from distant galaxies was shifted toward the red end of the spectrum. This meant they were moving away from us. The universe wasn't static. It was expanding. And if it was expanding now, it must have been smaller in the past. Rewind far enough, and you reach a beginning. Ironically, the name Big Bang was coined by a critic. Astronomer Fred Hoyle used the term dismissively on radio in 1949. He thought it sounded ridiculous, but the name stuck. And today, it's how we describe the cosmic birth. The most convincing evidence came by accident. In 1964, astronomers Penzias and Wilson were working with a massive horn antenna. No matter where they pointed, they heard a persistent hiss, a faint microwave signal coming from everywhere. They checked everything. They even evicted pigeons nesting in the antenna. But the hiss remained. Just 40 miles away at Princeton, physicists were building an antenna to look for that exact signal. But a phone call changed everything. Penzias and Wilson had already found it. They had been scooped. That hiss was the cosmic microwave background, the afterglow of the Big Bang itself. Light traveling for 13.8 billion years. Satellites would later map this radiation, revealing the seeds from which all galaxies and stars would eventually grow. Before the Big Bang, there was the singularity. All the matter and energy that would ever exist was compressed into a point smaller than a single atom. Temperatures were unimaginable, trillions of degrees. Densities were infinite. Time itself hadn't begun. This is where physics breaks down. Then something happened. At Planck time, the smallest moment physics can describe, the universe began to expand. Not slowly, but exponentially. In a fraction of a second, it grew from smaller than a proton to something macroscopic. This was the era of cosmic inflation. In the first moments, all the forces of nature were unified into one superforce. But as the universe expanded and cooled, they split apart. First gravity separated, then the strong nuclear force, then the weak force and electromagnetism. The laws of physics were being written in real time. In the earliest moments, the universe was a sea of particles and antiparticles. Every time they met, they annihilated in a flash of pure energy. By all rights, they should have canceled each other out. But somehow, for every billion pairs, one extra particle survived. That tiny imbalance is why we're here. For the first microsecond, the universe was filled with a quark gluon plasma, a hot, dense soup of fundamental particles. Then, as the temperature dropped, they began to combine, quarks sticking together to form protons and neutrons, the building blocks of atomic nuclei. The first 3 minutes were the most productive in cosmic history. As the universe expanded and cooled, protons and neutrons began to form. They jostled and collided, constantly being created and destroyed. The ratio of protons to neutrons was set, about 7-to-1, determined by the precise physics of particle interactions. Then came nucleosynthesis, the formation of the first atomic nuclei. Protons and neutrons began to fuse, creating deuterium, helium, and trace amounts of lithium. For about 3 minutes, the universe was a fusion reactor, converting hydrogen into helium. But as it expanded and cooled, the density dropped, and fusion stopped. The universe was now about 75% hydrogen and 25% helium, exactly what we observe in the oldest stars today. All the heavier elements, carbon, oxygen, iron, gold, would have to wait for stars to form. After nucleosynthesis, the universe entered a period of darkness. For hundreds of millions of years, there were no stars, no galaxies, just an expanding cloud of hydrogen and helium gas, slowly cooling. The cosmic microwave background had been released. The universe was transparent, but it was also empty. This was the cosmic dark ages. As the universe evolved, gravity continued to work its magic. The tiny fluctuations in density grew into a vast cosmic web, filaments of dark matter and gas stretching across billions of light years, with enormous voids of emptiness between them. At the intersections of these filaments, the densest regions, galaxies began to form. Galaxies are the building blocks of the universe, vast collections of stars, gas, and dust bound together by gravity. The first galaxies were small and chaotic, merging and growing over time. Some became beautiful spirals like our Milky Way. Others became elliptical balls of stars, the result of violent mergers. As galaxies grew, they pulled in more gas, forming new stars. Our own galaxy, the Milky Way, began forming about 13 billion years ago, just a few 100 million years after the Big Bang. It started as a clump of dark matter and gas. It merged with smaller galaxies, grew in size, and developed its familiar spiral arms. By the time our sun was born, 4.5 billion years ago, the Milky Way was already ancient. At the centers of many galaxies lurked monsters, supermassive black holes, millions or billions of times the mass of our sun. As gas fell into these black holes, it heated up and glowed brilliantly, creating quasars, the brightest objects in the universe. A single quasar can outshine an entire galaxy. These cosmic beacons shine across billions of light years, telling us about the early universe. But the universe wasn't perfectly smooth. Tiny fluctuations in density meant that some regions were slightly denser than others, and gravity, ever patient, began to work. Over millions of years, these denser regions pulled in more matter, growing denser still. The cosmic web began to form, filaments of gas stretching across the universe, with voids of emptiness between them. Around 200 million years after the Big Bang, something incredible happened. In the densest regions of gas, gravity finally won. Clouds collapsed, temperatures soared, and nuclear fusion ignited. The first stars were born, population 3 stars. They were monsters, hundreds of times more massive than our sun, burning at unimaginable temperatures. They lived fast and died young. Inside these first stars, alchemy happened. Nuclear fusion created heavier elements from lighter ones. Hydrogen fused into helium, helium into carbon, carbon into oxygen, neon, magnesium, silicon, all the way up to iron. For the first time, the universe had heavy elements. When a massive star runs out of fuel, its core collapses catastrophically. Then, in a fraction of a second, it rebounds. A titanic explosion, a supernova. For a brief moment, it outshines an entire galaxy. In that explosion, gold, silver, and uranium are forged. The supernova scatters these treasures across space, seeding the cosmos with the raw materials for planets, for life, for us. The death of the first stars made possible the birth of everything else, their remains mixed with the primordial gas. And from these clouds, new stars formed, stars with planets, stars that could one day host life. The iron in your blood, the oxygen you breathe, all of it was made inside stars that lived and died billions of years ago. We are, quite literally, stardust. 5 billion years ago, in a quiet spiral arm of the Milky Way, a cloud of gas and dust began to collapse. Perhaps triggered by a nearby supernova, the cloud fragmented. Pressure rose until nuclear fusion ignited. Our sun was born. Around the newborn sun, the remaining gas and dust swirled in a disk. Particles collided and stuck, growing into larger bodies. In just a few million years, these planetesimals had grown into protoplanets. It was a chaotic time of collisions and mergers. Earth formed about 4.5 billion years ago. But at first, it was anything but habitable. The surface was molten, a hellscape of magma. Asteroid impacts were constant. It was a violent beginning for a world that would one day teem with life. Early in its history, Earth suffered a catastrophic collision. A Mars-sized protoplanet, Theia, slammed into our world, vaporizing itself and blasting debris into orbit. Over time, this coalesced into the Moon. It stabilized our climate and created tides. Where did Earth's oceans come from? Evidence points to comets and water-rich asteroids that bombarded the early Earth. As Earth cooled, this water condensed into the first oceans. The stage was set for life. Life continued to evolve. Fish grew legs and crawled onto land. Reptiles dominated, then dinosaurs. Mammals, small and nocturnal, scurried in the shadows. When an asteroid struck 66 million years ago, wiping out the dinosaurs, mammals saw their chance. They diversified and spread. Among the mammals, one group, the primates, took a path that would lead to us. From small tree dwellers, they evolved. Around 6 million years ago, our ancestors stood up and walked on 2 legs. It was a small change with enormous consequences. Freeing the hands allowed tools, fire, and eventually civilization. Homo sapiens, our species, appeared about 300,000 years ago in Africa. We weren't alone, but we survived. Perhaps our capacity for abstract thought and language is why. We spread across the globe, becoming the most successful species. Then came agriculture, cities, writing, and everything we call civilization. In a cosmic blink, we went from hunter-gatherers to building skyscrapers, flying to the moon and sending probes to other planets. And through it all, we never stopped asking the biggest questions. Where did we come from? How did it all begin? Those questions led us back, all the way to the beginning, the Big Bang, the moment everything began. No one knows exactly how life began, but we have clues. Deep in the oceans, near hydrothermal vents, chemicals spewed from Earth's interior. In the warm, mineral-rich water, simple organic molecules formed. Amino acids, the building blocks of proteins, assembled themselves. And somehow, in a process we're still trying to understand, these molecules organized into the first living cells. The first life was microscopic, single-celled organisms that floated in the oceans. They were simple, but they were alive. They could replicate, they could evolve. For billions of years, these simple cells were the most advanced life on Earth. About 2.5 billion years ago, something remarkable happened. A type of bacteria called cyanobacteria evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into energy, releasing oxygen as a waste product. At first, oxygen was toxic to most life. It caused a mass extinction. But over time, organisms evolved to use it. For 3 billion years, life remained microscopic. Then, around 541 million years ago, everything changed. In a burst of evolution called the Cambrian explosion, most major animal groups appeared in the fossil record. The seas filled with strange and wonderful creatures, trilobites, anomalocaridids, and the ancestors of everything that would follow. Life had become complex. The universe is still expanding. In fact, the expansion is accelerating. Something is pushing the cosmos apart. We call it dark energy. We don't know what it is, but it makes up 68% of the universe, and it will determine our cosmic fate. There are 3 possibilities. The Big Crunch, gravity wins. The Big Rip, dark energy tears everything apart. Or the most likely, the Big Freeze. If expansion continues, the universe will grow cold and dark. Trillions of years from now, the last new star will be born. The remaining stars will burn out. The universe will be filled with the corpses of stars, white dwarfs, neutron stars, and black holes. Eventually, matter itself will decay. The universe will enter the black hole era. Only these gravitational monsters will remain. But even they are not eternal. Over unfathomable eons, they will evaporate through Hawking radiation, particle by tiny particle. Finally, the last black hole will vanish in a flash of light. The universe will reach heat death, maximum entropy. No light, no life, no time, just an eternal empty silence. The story of everything is over.
This is Alaknanda, a massive, grand design spiral galaxy located 12 billion light-years from Earth. At first glance, it looks ordinary, beautiful, but ordinary. But here's what makes it extraordinary. We're seeing it as it existed just 1.5 billion years after the Big Bang. According to everything astronomers thought they knew, this galaxy should not exist. In the early universe, galaxies were supposed to be messy,
chaotic, clumpy collections of gas and stars, still finding their shape. But Alaknanda looks like it belongs in the modern universe, alongside galaxies billions of years older. It has two sweeping spiral arms wrapped around a bright, round central region. It's organized, it's mature, and it's breaking all the rules. In late 2025, two astronomers from the National Center for Radio Astrophysics in Pune, India, Rashi Jain and Yogesh Wadadekar, were studying images from the James Webb Space Telescope. They were examining data from 21 different filters, dissecting light from the early universe, and then they found something that made them stop. A galaxy so perfectly formed, so unexpectedly mature, that it challenged everything they thought they knew about cosmic history. Rashi Jain and Yogesh Wadadekar spend their days studying the cosmos from Pune, India. Using the most powerful space telescope ever built, the James Webb Space Telescope, they were peering back in time, hoping to understand how galaxies formed in the universe's infancy. What they found would make headlines around the world. The James Webb Space Telescope is uniquely powerful. Its infrared vision allows it to see through cosmic dust and look further back in time than any telescope before. For their study, Jain and Wadadekar used 21 different filters, each one capturing a different wavelength of light. Together, these images would reveal the true nature of a galaxy from the dawn of time. They named it Alaknanda, after the Himalayan river that serves as one of the headstreams of the sacred Ganga. Why this name? Because the Alaknanda River is the sister of the Mandakini, and Mandakini is the Hindi name for our own Milky Way galaxy. Just as the rivers are connected in the mountains, this distant spiral is connected to our cosmic home. A poetic name for a poetic discovery. Alaknanda lies at a redshift of about 4, meaning its light has been traveling for more than 12 billion years to reach us. We are seeing this galaxy as it appeared just 1.5 billion years after the Big Bang. The universe was only 10% of its current age. And yet, here was a galaxy that looked remarkably similar to our own Milky Way, which is 10 billion years older.
Elon Musk has a vision, not a colony, not an outpost, a city, 1 million people living on Mars, a self-sustaining civilization, a second home for humanity. It sounds like science fiction. But SpaceX is already building the ships that will take us there. This is the plan. This is how they'll do it. A city on Mars. This is how we become a multi-planetary species. 1 million people. This is the greatest challenge humanity has ever faced. The hardest thing. Elon Musk has been clear about his goal. Not just to visit Mars, to stay, to build a city, to create a self-sustaining civilization that can survive even if Earth is cut off. A backup drive for humanity, a second Genesis, a second home. We need to become a multi-planetary species. Civilization needs a backup drive. In this documentary, we'll explore the complete SpaceX plan for Mars, from the starship that will take us there to the propellant plant that will bring us home, from the first habitats to the million-person city, from the challenges to the triumphs. This is how SpaceX will build our city on Mars. Why Mars? Because Earth is fragile. A single asteroid, a supervolcano, a nuclear war could end civilization. We have no backup. Mars is the only planet in our solar system that could support human life. It's our insurance policy. Stephen Hawking said, spreading out may be the only thing that saves us from ourselves. Why not the moon? The moon has no atmosphere, 14-day nights, no water ice in useful quantities, and gravity 1/6 of Earth's. Mars has a 24-hour day, a thin atmosphere, water ice in abundance, and 38% of Earth's gravity, low enough to make launches easy, high enough to raise healthy children. Mars has everything we need to survive: water ice to drink, to grow food, to split into hydrogen and oxygen for rocket fuel, carbon dioxide to grow plants, iron, aluminum, and silicon to build. Mars isn't just a destination, it's a home.
Starship is the largest rocket ever built. It stands 120 meters tall, taller than the Statue of Liberty. It weighs 5,000 tons fully fueled. Its 33 Raptor engines generate 16 million pounds of thrust. It can lift 100 tons to the moon, 100 tons to Mars, 100 tons anywhere. Its 33 Raptor engines generate 16 million pounds of thrust. This is the heart of the interplanetary transport system. Taller than any rocket in history, its scale is hard to comprehend until you see it against our greatest monuments. Built for one purpose, to make life multi-planetary, it is the most powerful rocket ever built. The key to Mars is reusability. Without it, the cost of space travel remains prohibitive. The Super Heavy booster lands back on Earth, precision-guided to its launch mount for rapid turnaround. Starship continues to orbit while the booster is already being prepared for its next flight. Starship lands on Mars, refuels, and flies back. Each ship can be used dozens of times. The cost per launch drops from billions to millions. Mars becomes affordable for the first time in history. Elon Musk notes, if Starship is fully reusable, the cost per launch drops to around $2 million. That makes Mars possible. Each Starship can carry 100 tons to Mars, a payload capacity that changes the nature of exploration. Inside are habitats, rovers, solar panels, and construction equipment, the building blocks of a new civilization. In each launch window, every 26 months, SpaceX plans to send 10 to 20 Starships. That's 1,000 to 2,000 tons of cargo per window, enough to build a city on another planet. To get to Mars, Starship needs to refuel in orbit. This is the critical step in the journey. A tanker Starship launches, docks with the crew Starship, and transfers propellant. It's a delicate dance in zero-G. It takes about 10 tanker flights to fully fuel one crew Starship. Once the tanks are topped off, the mission begins. Fully fueled and ready for the long journey ahead, then it's off to Mars. Our future among the stars begins now.
Mars and Earth only align for a Mars mission every 26 months. During these windows, Starships launch in waves. The journey takes about 6 months. Then the window closes and they wait for the next one. Starship is designed for 100 passengers, private cabins, exercise areas to maintain muscle and bone mass, common spaces to socialize, windows to watch the stars. For 6 months, this is home. The journey has dangers, cosmic radiation, microgravity. The ship has a storm shelter for solar flares. Passengers exercise 2 hours daily to maintain muscle and bone. By the time they arrive, they're ready to work.
Before the first humans arrive, cargo starships will land. They'll carry solar panels, habitats, rovers, and critical life support systems. They'll land autonomously, preparing the site with robotic precision. When the crew finally arrives, their home and infrastructure are already waiting. The first starships land in a circle, creating a protected landing zone. Their cargo bays become the first storage units. Their fuel tanks become reservoirs. The ships themselves become the very first structures of the Martian base. The first crew lands. They step onto Martian soil for the first time in history. They've been training for years. Now the real work begins. They unload cargo and set up habitats. The foundations of the first city are laid. The first city has begun. Prepare for the next wave.
Starship can't return to Earth with fuel from Earth. The fuel is too heavy. It must be made on Mars. That's the key to the entire plan. If we can make fuel on Mars, starships can fly back. Mars becomes accessible. The Sabatier process combines carbon dioxide from the Martian atmosphere with hydrogen from water ice. It produces methane, the fuel Starship uses, and oxygen. The oxygen is used as oxidizer. Water is recycled. The propellant plant is the heart of the city. It produces fuel for starships. Each starship needs 1,000 tons of methane and oxygen. The plant runs on solar power. It produces fuel continuously. When the launch window opens, starships are ready.
The first habitats are inflatable. They're lightweight, compact for transport. Once deployed, they expand. A 3D printer then covers them with Martian soil, regolith, for radiation protection. Each habitat becomes a home. Mars has no magnetic field, no thick atmosphere. Radiation is a constant threat. The habitat's regolith shell provides protection, 2 to 3 meters of Martian soil above the living space. Inside, it's as safe as Earth. Future habitats will be underground. Mars has lava tubes, natural caverns formed by ancient volcanic activity. These provide natural radiation protection. We'll seal them, pressurize them, and build cities inside.
The Martian atmosphere is 95% carbon dioxide. A life support system extracts oxygen from CO2. It adds nitrogen from the atmosphere. The result is breathable air. Recycled, clean, always available. Mars has water ice in abundance, at the poles and buried beneath the surface at mid-latitudes. We drill, we melt, we filter. The water is pure. It's for drinking, for growing food, for making fuel. Food is grown in hydroponic greenhouses. Plants grow in nutrient-rich water, not soil. LED lights provide the perfect spectrum. The first crops: potatoes, lettuce, tomatoes, wheat. Within a few years, the colony is self-sufficient in food.
Mars gets about half the sunlight Earth does. Solar panels work, but they're less efficient. And dust storms can cover them, cutting power for weeks. Solar is part of the solution, but not the whole solution. Dependency on the sun alone creates a vulnerability for a growing colony. We need a constant heartbeat of energy. NASA's kilopower reactor is designed for Mars. It's small, safe, and provides constant power. 10 kilowatts per unit. A cluster of reactors can power a whole city, providing a reliable energy baseline. Nuclear power works through dust storms, through the night, through anything the red planet throws at us. It is the unwavering foundation of the Martian power grid, ensuring survival regardless of the weather. Energy storage is critical. Batteries store excess power from the day for heavy nighttime demand. Hydrogen produced from water can be burned for heat or used in fuel cells during emergency outages. This synergy of nuclear, solar, and storage creates a system that is redundant, reliable, and resilient. The Martian city doesn't just survive, it thrives on a power grid built to endure for generations.
The first wave is small, 100 people. They're engineers, scientists, medics, builders. Their job? Build the infrastructure, the propellant plant, the habitats, the greenhouses. They prepare for the next wave. Every 26 months, more starships arrive, thousands of colonists. The outpost becomes a settlement, a town. Streets, shops, schools. A new society begins to flourish under the Martian sky. By 2050, the city has 100,000 people. Sleek underground tunnels connect the sprawling habitats. Pressurized domes create outdoor spaces. Automated factories produce essential goods for the colony. Schools teach Martian-born children. A new civilization is born. By the 2060s, the city reaches 1 million people. It's self-sustaining. Towers, parks, plazas. Starships coming and going. A thriving Martian metropolis. It can survive without Earth. It's a backup drive for humanity. A second home among the stars.
The first child born on Mars will be a Martian. They'll never know Earth's gravity, Earth's sky, Earth's oceans. They'll grow up in domes and tunnels. Mars is now their only home. A new culture will emerge. Martian art, Martian music, Martian fashion, shaped by the red landscape, the thin atmosphere, the struggle for survival. A new branch of humanity. Language will change. Cut off from Earth for generations, Martian English will evolve new words, new accents. Earthlings and Martians might struggle to understand. Earthlings and Martians might struggle to understand each other.
When astronomers talk about our galactic neighborhood, they focus on the two giants, Andromeda, the largest, and our own Milky Way. But there's a third member of this cosmic family that deserves just as much attention. The Triangulum Galaxy, also known as Messier 33, is the third largest galaxy in the local group. It's a beautiful face-on spiral, oriented perfectly so we can study its structure in exquisite detail. At 273 million light-years away, it's one of the most distant objects visible to the naked eye. And it holds secrets that are changing how we understand galaxy formation, star birth, and the dynamics of our cosmic neighborhood. This is the story of the Triangulum Galaxy, the overlooked giant that's finally getting its moment in the spotlight. Why study Triangulum? 3 reasons. First, its orientation. It's almost perfectly face-on from our perspective, giving astronomers a clear, unobstructed view of its spiral structure, star-forming regions, and the distribution of stars and gas. Second, it's different from its larger neighbors. Unlike the Milky Way and Andromeda, which are barred spirals, Triangulum has no central bar. Its arms emerge directly from its core. And third, it may hold clues to a fundamental question. Why do some galaxies have supermassive black holes at their centers, while others apparently don't? In this documentary, we'll explore every facet of the Triangulum Galaxy, from its discovery by a little-known Italian astronomer in the 1600s, to the latest Hubble mosaics revealing 25 million individual stars. From its massive star-forming region NGC 604, 40 times larger than the Orion Nebula, to its mysterious lack of a central supermassive black hole. From its possible status as a satellite of Andromeda, to the stream of hydrogen gas that connects them. This is the complete story of the third giant of the local group. The story begins in the 17th century with a little-known Italian astronomer and priest named Giovanni Battista Hodierna. Before 1654, he published a work called De Systemate Orbis Cometici, in which he listed several nebulous objects he had observed. Among them was a cryptic entry, near the triangle Hinc Inde, a reference to the constellation Triangulum. Most historians believe this was the first recorded observation of the Triangulum Galaxy. For nearly 150 years, this discovery remained obscure, known to few. On the night of August 25, 26, 1764, the French astronomer Charles Messier was doing what he did best, searching for comets. He kept finding fuzzy objects that could be mistaken for comets, so he decided to catalog them to avoid confusion. On that night, he independently rediscovered Hodierna's object and added it to his list as entry number 33. The name M33 stuck. Messier described it as a nebula without stars. His telescopes weren't powerful enough to resolve its true nature. When William Herschel compiled his massive catalog of nebulae, he generally avoided including objects already listed by Messier, but M33 was an exception. On September 11, 1784, he observed and cataloged it as HV17. More importantly, he noticed something within the galaxy, an unusually bright patch that he cataloged separately as H3 150. This patch would later receive its own NGC designation, NGC 604. Herschel had discovered the most spectacular star-forming region in the local group without even knowing it. In the mid-19th century, Irish astronomer William Parsons, the 3rd Earl of Ross, built the largest telescope of his era, a 72-inch reflector known as the Leviathan. With it, he observed several spiral nebulae and made detailed sketches. In 1850, his assistant R.J. Mitchell produced a drawing of M33 showing its spiral arms. Mitchell described it as full of knots with two similar curves like an S cross in the center. This was among the first evidence that some nebulae had spiral structure, a clue that they might be separate island universes like our own Milky Way. The early 20th century saw the great debate over the nature of spiral nebulae. Were they gas clouds within the Milky Way or separate galaxies entirely? In 1922-23, astronomers John Charles Duncan and Max Wolf discovered variable stars in M33. But it was Edwin Hubble who delivered the decisive blow. In 1926, he identified 35 of these variables as classical Cepheids, stars whose intrinsic brightness varies in a predictable way with their pulsation period. By measuring their apparent brightness, he could calculate their distance. The result was unambiguous. M33 was far beyond the Milky Way. M33 was an independent stellar system, an island universe. The debate was over. In the Hubble classification system, Triangulum is designated SAS.CD. Let's break that down. The S means it's a spiral galaxy. The A indicates it has no central bar, unlike the Milky Way and Andromeda, which are barred spirals classified as SB. The S means the spiral arms emerge directly from the nucleus rather than from an inner ring, and the CD suffix places it at the open end of the spiral sequence, meaning its arms are relatively loosely wound. One of Triangulum's greatest gifts to astronomers is its orientation. It's tilted at an angle of about 54 to 56 degrees to our line of sight. That's nearly face-on, giving us an unobstructed view of its spiral structure without significant obscuration by gas and dust. Unlike edge-on galaxies where spiral arms are hard to trace, Triangulum presents its full glory for us to study. It's the perfect laboratory for understanding how spiral galaxies are structured. Lord Ross's 19th century sketch described M33's arms as two similar curves like an S-cross in the center. Modern images reveal far more detail. The arms are thick and clumpy, dotted with blue star clusters and pink nebulae. The arms are less tightly wound than those of Andromeda or the Milky Way, giving the galaxy a more open, relaxed appearance. At the center of Triangulum lies a bright nucleus, classified as an H2 nucleus because of its ionized hydrogen emission. But here's the surprising part. Unlike most large galaxies, Triangulum lacks a central bulge. It also lacks a supermassive black hole at its heart. The core region is simply the innermost part of the disk, with stars orbiting in a relatively flat plane rather than a three-dimensional bulge. Like many spiral galaxies, Triangulum's disk isn't perfectly flat. Out to a radius of about 26,000 light-years, the disk is warped. This warp is likely caused by gravitational interactions with other galaxies. The warp is subtle, but it tells us that Triangulum is not an isolated, undisturbed galaxy. It's feeling the gravitational pull of its massive neighbor, Andromeda.
Tense, dramatic voice. 4 months after Neil Armstrong took that one small step, America was ready to go back. Apollo 12 was supposed to be routine, the second moon landing, a demonstration that we could do this regularly. But the weather had other plans. As the Saturn V lifted off, it flew directly into a thunderstorm. 36 seconds later, lightning struck. Then it struck again. In mission control, every alarm went off. The capsule lost power. Telemetry went dead.
For a terrifying moment, it seemed like the mission was over before it had truly begun. This is the story of Apollo 12, the mission that almost didn't make it, and the crew that refused to give up. The crew of Apollo 12 was different. Where Armstrong was reserved and professional, Pete Conrad was outgoing, irreverent, and funny. He'd made a bet with a reporter that he'd say something spontaneous when he first stepped on the moon, and he delivered. Dick Gordon was a naval aviator with ice in his veins. Al Bean was an artist at heart. He'd later become a painter. Together, they brought a new energy to space exploration. They'd need every bit of that attitude when things went wrong. Apollo 11's landing was historic, but it wasn't precise. Apollo 12 had a different goal, precision. Their target was Surveyor 3. If they could land within walking distance, they could retrieve parts from it. The first time humans visited an alien spacecraft. The target was tiny, just a few meters across. Hitting it from 250,000 miles away required unprecedented accuracy. This is the complete story of Apollo 12, from the terrifying lightning strikes that nearly ended the mission, to the pinpoint landing that proved we could navigate to another world. This proved Apollo wasn't a fluke. November 14, 1969, Launch Day. The weather at Kennedy Space Center was terrible. Rain, low clouds, and storms building. The launch window was narrow. If they missed it, the mission would be delayed for months. The decision was made to go. The Saturn V could fly through rain, they reasoned. Lightning was a concern, but they didn't realize they might trigger it. At 11:22 a.m., the Saturn V roared to life and lifted off, climbing into the overcast sky. Rain lashed the windows. Inside, Pete Conrad, Dick Gordon, and Al Bean monitored their instruments, feeling the vibration of the most powerful machine ever built. 36 seconds after launch, the Saturn V triggered a lightning strike. The bolt hit the rocket and followed its plume. In the capsule, every warning light came on. Fuel cells dropped offline. In mission control, telemetry went dead. Al Bean later said, all of a sudden, the control panel just lit up like a Christmas tree. The spacecraft was trying to tell us something was wrong. Before anyone could react, a second lightning bolt struck. This one was even more damaging. The guidance platform was lost. The command module was running on backup power, and the Saturn V was still climbing, carrying them toward orbit with no control. In mission control, chaos reigned. But one man, John Aaron, noticed something strange in the voltage readings. He remembered a pattern from a simulation months earlier. He said, "Flight, try SCE to aux." Aaron recalled, "It was just one of those things. I'd seen it in a simulation, and it stuck in my memory." In the capsule, Al Bean heard the call. He found the obscure switch and flipped it. Instantly, telemetry returned to normal. The fuel cells came back online. The spacecraft was alive again. They'd been saved by a 26-year-old's memory. Pete Conrad later said, "I didn't know what the hell he was talking about, but Al found the switch, and John Aaron saved our mission." The lightning strikes were over, but their effects lingered. The spacecraft's guidance platform, the heart of its navigation system, was spinning uselessly. The crew would have to perform a manual realignment, using the stars to re-establish their orientation, a procedure they'd never practiced under these conditions. For the next few hours, the crew worked methodically, using a sextant to sight stars and feed their positions into the computer. It was like navigating an ocean ship in the 18th century, except they were traveling at 25,000 miles per hour, 250,000 miles from Earth. Slowly, painstakingly, they rebuilt their navigation solution. By the time they were ready for translunar injection, they had their orientation back. With navigation restored, it was time for the translunar injection burn, the critical engine firing that would send them to the moon. The SIVB stage fired for nearly 6 minutes, accelerating them to escape velocity. They'd survived the lightning. Now they had a mission to complete. As they left Earth behind, the crew took a moment to appreciate the view. No borders, no divisions, just one planet, one home. It's a view that changes everyone who sees it. Pete Conrad, never one for sentimentality, was quiet for a moment. Then he got back to work. 3 days after launch, they arrived at the moon. They were now in orbit around another world, only the second crew to achieve this feat. The service module engine fired for exactly the right duration, slowing them enough to be captured by lunar gravity. Somewhere down there, Surveyor 3 was waiting. For the next day, they orbited the moon, studying their landing site. The target was a spot in the Ocean of Storms, about 1,000 feet from Surveyor 3. It was the most precise landing target ever attempted. If they missed by even a few hundred feet, they'd be too far to walk to the robot. The moment came for separation. Pete Conrad and Al Bean floated through the tunnel into the lunar module, intrepid. They were on their own now. With a gentle push from springs, they separated from the command module. Dick Gordon would stay behind while his crewmates descended. Powered descent initiation. The engine fired, slowing them from orbital velocity and beginning the long drop to the surface. Below, the moon rushed up at terrifying speed. Pete Conrad had his eyes on the landing site, ready to take manual control. Al Bean called out altitudes and velocities. They were aiming for a spot 1,000 feet from Surveyor 3, a precision landing. Landing on the moon is incredibly difficult. There's no GPS, no atmosphere. Intrepid's landing radar sent pulses toward the surface. The computer compared the data to preloaded maps, calculating the descent profile. Pete Conrad watched out the window. In the final seconds, dust erupted around them, a cloud of razor-sharp particles. Pete Conrad couldn't see the surface. He was flying blind, relying entirely on his instruments. But he'd trained for this. He trusted the computer, his crewmate, and the engineers. Then, contact. Probes touched the surface, signaling the engine to shut down. Dust settled. Silence returned. Pete Conrad looked out the window and saw exactly what he'd hoped to see. Surveyor 3, sitting quietly about 600 feet away. They'd hit their target with unbelievable accuracy. "Hey, there it is!" he exclaimed, "right where it's supposed to be!" When Pete Conrad stepped onto the moon, he remembered his bet with a reporter that he'd say something spontaneous. He grinned and said, "Whoopee, man, that may have been a small one for Neil, but it's a long one for me." Classic Pete Conrad. Al Bean followed soon after, becoming the 4th human to walk on the moon. He was overjoyed. This was the moment he'd dreamed of. Together, they set up the flag, took the obligatory photos, and got to work. There were experiments to deploy and samples to collect. But not everything went smoothly. Al Bean was setting up the color TV camera, supposed to broadcast live from the moon. In his excitement, he accidentally pointed it directly at the sun. The intense light burned out the sensor instantly. The feed died. Millions saw nothing but static. Bean was devastated. "I pointed it at the sun," he said. "I thought it would be okay, but it wasn't." But there was still work to do. Their primary goal was to reach Surveyor 3, about 600 feet away, a significant trek on the moon. When they reached Surveyor 3, they stood for a moment, taking it in. A robot from Earth waiting for them for 2.5 years. Working carefully, they removed components, the TV camera, the soil scoop. They bagged them to bring back to Earth, the ultimate salvage mission.
On September 6, 2023, a pulse of gamma rays washed over Earth. It lasted less than a second, but in that fraction of a moment, it carried more energy than our sun will produce in its entire lifetime. This was GRB 230906A, a short gamma ray burst, the signature of one of the most violent events in the universe. For 2 years, astronomers studied it. They traced it back 8.5 billion light-years to a tiny galaxy in a stream of debris. And what they found changed our understanding of where gold, platinum, and the heavy elements in our bodies come from. This is the story of GRB 230906A. Every piece of gold you've ever seen, every wedding ring, every necklace, every bar in a vault, was forged in a cosmic catastrophe like this one. Neutron star collisions are the universe's factories for heavy elements. They create gold, platinum, uranium, and dozens of other elements through a process called rapid neutron capture. This could be an indication that tidal interaction between galaxies can trigger star formation, and 2 neutron stars can end up merging. In this documentary, We'll take you through the complete story of GRB 230906A, from its initial detection to the painstaking multi-telescope investigation that followed, from the physics of neutron stars to the chemistry of gold. And we'll explore the profound implications, not just for understanding the universe, but for understanding where we come from. Gamma-ray bursts were discovered by accident. In the 1960s, the US launched the Vela satellites to monitor for Soviet nuclear tests. Instead, they found something far stranger: brief, intense flashes of gamma rays coming from deep space. For decades, their origin remained a mystery. Astronomers didn't know if they were from our galaxy or the edge of the universe. For 30 years, astronomers didn't know what caused gamma-ray bursts. Astronomers now know there are two main types of gamma-ray bursts. Long GRBs last more than 2 seconds and come from the collapse of massive stars, hypernovae. Short GRBs last less than 2 seconds and come from the merger of compact objects, neutron stars or black holes. GRB 230906A was a short burst, lasting just 0.9 seconds. That told astronomers immediately what they were dealing with. The energy released in a gamma-ray burst is almost incomprehensible. In just seconds, a GRB releases as much energy as the sun will produce over its entire 10 billion year lifetime. These are the most powerful explosions in the universe since the Big Bang itself, and GRB 230906A was one of them.
To understand GRB 230906A, you must first understand neutron stars. When a massive star explodes as a supernova, its core collapses into an incredibly dense object, a neutron star. These are the densest objects in the universe outside of black holes. A single teaspoon of neutron star material would weigh billions of tons. Neutron stars are small stars about 15 kilometers in diameter, with 1.5 times the mass of the Sun. They are extremely dense. Many massive stars are born in binary systems. When both explode as supernovae, they leave behind two neutron stars locked in a gravitational dance. Over hundreds of millions of years, they lose energy through gravitational waves and spiral closer together. Eventually, they touch, and when they do, the result is catastrophic. When two neutron stars occasionally collide with one another, they can produce important elements like gold and platinum and generate gravitational waves that ripple across space. When two neutron stars merge, they produce a kilonova, a brilliant explosion that outshines entire galaxies. This explosion is so energetic that it creates the conditions for rapid neutron capture, the R process, which forges heavy elements like gold, platinum, and uranium. The merger also produces a short gamma-ray burst, like GRB 230906A. Such explosions generate kilonova emissions, bright halos of light that are one of the main sites of heavy element production in the universe. On September 6, 2023, at 12:55 UTC, the Fermi Gamma Ray Space Telescope detected a burst of high-energy gamma rays. It was brief, lasting just under a second, but incredibly intense. It was designated GRB 230906A. The automated systems alerted astronomers around the world. The hunt was on. Fermi GBM detected a short gamma-ray burst. The initial data showed a multi-peak structure, with the main burst lasting about 0.9 seconds. This was characteristic of a short GRB, the signature of a neutron star merger. But to learn anything more, astronomers needed to pinpoint its exact location. That would require more telescopes. The Fermi GBM light curves in two energy bands showed hard X-rays and gamma rays. Fermi alone couldn't provide a precise location. But other spacecraft also detected the burst: CONUS Wind, Astrosat, and others. Together, they formed the Interplanetary Network, triangulating the burst's position to a region of the sky. Within hours, other observatories began turning toward that region. SWIFT is designed for exactly this kind of event. Within hours, it began targeted observations of the GRB's location. Its X-ray telescope detected a faint X-ray source, the afterglow of the explosion. But the localization wasn't precise enough to identify a host galaxy. SWIFT has initiated a TOU observation of the IPN GRB 230906A. Automated analysis of the XRT data will be presented online. The hunt was on, but the target remained elusive within a broad field of stars. SWIFT's UV optical telescope looked for an optical afterglow,
It found nothing down to a limiting magnitude of 22.8. This was a clue. The burst might be very distant, or the afterglow might be very faint, or both. No optical afterglow consistent with the XRT position is detected in the initial UVOT exposures. The silence in the optical spectrum hinted at a phenomenon occurring at the very edge of the observable universe. Swift's XRT gave an approximate position, but to find the host galaxy, astronomers needed much greater precision. They needed the sharpest X-ray eyes in the sky, the Chandra X-ray Observatory. Without the Chandra X-ray Observatory, the faint host galaxy might have been overlooked entirely. Chandra represents the pinnacle of resolution, capable of seeing what all others miss. Chandra X-ray Observatory has the highest resolution of any X-ray telescope ever built. On September 11, 2023, it was pointed at the location of GRB 230906A for a 19.8 kilosecond observation. We carried out a Chandra target of opportunity observation using the ASIS-S camera with a total exposure of 19.8 ksothers. Within that data, astronomers found exactly what they were looking for. At the location Swift had identified, Chandra detected a clear X-ray source. It showed signs of fading, a classic afterglow signature. The position was pinpointed to within 0.8 arcseconds, precise enough to identify the host galaxy. At the location of the Swift XRT candidate afterglow, we detect a clear X-ray source at the northeast edge of the XRT localization. This fading confirmed the nature of the event, a dying ember of a cosmic cataclysm. But here's where things got interesting. When astronomers looked at survey images of the Chandra position, they saw nothing. No bright galaxy, no obvious host. This was unusual. Short GRBs usually occur in galaxies. Where was this one? We note that there is no obvious host galaxy at this location in the Legacy survey, although multiple sources exist within a few arcseconds. The source had been found, but its home remained a ghost, a cosmic puzzle that demanded even more powerful eyes.
If there was a host galaxy, it had to be very faint. Astronomers turned to the Hubble Space Telescope for the deepest possible optical and infrared imaging. What they found surprised them. Once Chandra told them exactly where to look, researchers used Hubble to reveal something remarkable. The researchers then used Hubble to reveal a tiny, extremely faint galaxy at that exact position. Once Chandra told them exactly where to look, the researchers then used Hubble to reveal a tiny, extremely faint galaxy at that position. There it was, a tiny, faint galaxy, so dim that it had escaped detection in all previous surveys. It was located about 8.5 billion light-years away, meaning the light had been traveling for most of the universe's history. This was one of the faintest galaxies ever associated with a short gamma-ray burst. The Chandra data gave the researchers an even more accurate position, revealed a tiny, extremely faint galaxy at that position. At 8.5 billion light-years, GRB 230906A occurred when the universe was about half its current age. This is one of the most distant, short GRBs ever identified, and its host galaxy was unlike any GRB host seen before. Compared with standard GRB galaxies, its faintness, compact size, and color would suggest a high redshift host. The researchers noted that its faintness and color suggested a very distant, high redshift environment. The Hubble image revealed one tiny galaxy. But was it alone? Astronomers turned to the Very Large Telescope in Chile. Using its powerful MUSE spectrograph to study the region in greater depth, what they found was extraordinary. Those observations showed that the faint galaxy detected by the Hubble wasn't alone. It was part of a group of galaxies. The researchers found it was part of a group, a completely different environment than any previously identified GRB host. The faint galaxy wasn't isolated. It was part of a group, a collection of galaxies interacting with each other. These galaxies showed clear signs of gravitational disturbance and mergers. It was a chaotic cosmic dance. The researchers found that the GRB came from a galaxy in an extended tidal stream of gas, dust, and stars. This tidal stream was almost 600,000 light-years long, an immense structure formed by galaxy collisions. When galaxies interact, their gravity pulls material into long, thin streams called tidal tails. This group had a massive tidal stream stretching 600,000 light-years, 6 times the diameter of our own Milky Way. And within that stream, in a tiny galaxy formed from the debris, GRB 230906A occurred. The tiny galaxy that hosted this neutron star collision is embedded within a stream of gas that stretches some 600,000 light-years long. When galaxies collide, it seems destructive, but it's also creative. The gravitational forces compress gas, triggering waves of new star formation. The material pulled into tidal streams becomes the birthplace of new stars, and eventually, new neutron stars. This stream was likely created when a group of galaxies collided hundreds of millions of years ago, stripping gas and dust from the galaxies and tossing it into intergalactic space. The team reconstructed the timeline. About 700 million years ago, the galaxy group collided, triggering a burst of star formation in the tidal stream. Massive stars were born in binary systems. They lived fast and died young, exploding as supernovae and leaving behind neutron stars. Over hundreds of millions of years, those neutron stars spiraled together, and finally, in 2023, they merged. The team said they suspect the neutron stars that collided were born during a surge of star formation, triggered by the galactic merger roughly 700 million years ago. The team said they suspect the neutron stars that collided were born during a surge of star formation, triggered by the galactic merger roughly 700 million years ago. The researchers called it a merger within a merger. The galaxy collision set the stage. The neutron-star collision was the final act. This was the first time a short gamma-ray burst had been linked to such an environment. A tiny galaxy born from the debris of a larger collision. This is the first time astronomers associated this type of signal with such a large-scale galactic interaction. For decades, scientists wondered where the universe's heaviest elements come from. Hydrogen and helium were made in the Big Bang. Carbon and oxygen were made in stars. Iron is forged in supernovae. But elements heavier than iron, gold, platinum, uranium, require a different process. Neutron star mergers create kilonova explosions that foster what's called the R process. R process refers to rapid neutron capture, nuclear reactions that create about half of the atomic nuclei heavier than iron. The R process, rapid neutron capture, requires an environment with an enormous flux of neutrons. Neutron star mergers provide exactly that. In the violent collision, nuclei capture neutrons faster than they can decay, building up to the heaviest elements in the periodic table. Through a chain of nuclear reactions, a collision between two neutron stars can produce heavy elements like gold and platinum. Every atom of gold on Earth, every wedding ring, every necklace, every gold bar, was forged in an event exactly like GRB 230906A. The gold atoms that now adorn your body were scattered across space billions of years ago, eventually coalescing into the cloud that formed our solar system. The gold that we have on Earth was produced in an explosive event of this nature. The heavy elements in our body, like iron for example, come from about 10,000 stars. The iron in your blood was forged in supernovae. The oxygen you breathe was made in massive stars, and the trace amounts of gold in your body, yes, you have gold in you, came from neutron star mergers. We are not just stardust, we are neutron stardust. It took billions of years, but that iron persisted on Earth. And as our bodies formed and evolved, they used that material.
Astronomers had noticed a puzzle. Some stars in the outer regions of galaxies, far from where supernovae typically occur, contain surprisingly high amounts of heavy elements like gold. How did they get there? GRB 230096A may provide the answer. This latest discovery may help solve open questions as to how those precious elements are sometimes outside galaxies. GRB 230096A occurred in a tidal stream far from any major galaxy. When its neutron stars merged, they scattered heavy elements into intergalactic space. Those elements could later be incorporated into new stars forming in the stream. This could explain how gold and platinum end up in distant stellar populations. This discovery opens up a new possibility. Short GRBs might occur not just in large galaxies, but in tiny galaxies formed from tidal debris. Some previously hostless GRBs, events with no identified host galaxy, might actually be in these faint, overlooked systems. This discovery reveals new homes for these cosmic collisions. In about 4.5 billion years, our own Milky Way galaxy will collide with Andromeda. When that happens, tidal streams will form, new stars will be born, and billions of years later, neutron stars in those streams may merge, creating gamma-ray bursts, forging gold and platinum, and scattering heavy elements across intergalactic space. GRB 230906A taught us something profound. Destruction and creation are linked across cosmic scales. Galaxy collisions create tidal streams. Tidal streams create stars. Stars create neutron stars. Neutron stars merge and forge gold. And that gold ends up in planets, in life, in us. The next time you see a gold ring, remember where it came from. Not from a mine, not from the Earth's crust, but from the collision of dead stars in a distant galaxy 8.5 billion years ago. We are all made of cosmic violence. Thank you for joining us on this journey across 8.5 billion light years. If this story inspired you, share it. Comment below. What element in your body fascinates you most?
In the constellation Ursa Major, 12 million light years from Earth, a galaxy is in the midst of a violent crisis. It's called the Cigar Galaxy, or M82, and it's one of the most extreme objects in our cosmic neighborhood. While galaxies like our Milky Way form stars at a leisurely pace, about 1 or 2 new suns per year, M82 is in the grip of a furious starburst, churning out new stars at a rate 10 times higher. This explosive activity is literally blowing the galaxy apart, sending massive filaments of hydrogen gas streaming into space. And in 2014, it hosted the closest Type Ia supernova in decades, Supernova 2014J, a cosmic explosion that astronomers studied in unprecedented detail. This is the story of the Cigar Galaxy, a cosmic firestorm that's consuming itself from within. Why does the Cigar Galaxy hold such a special place in astronomy? 4 reasons. First, it's the closest example of a starburst galaxy, a galaxy undergoing an intense episode of star formation that consumes its gas at an unsustainable rate. Second, it's expelling this gas in a massive superwind that we can observe in exquisite detail, helping us understand how galaxies regulate their growth. Third, in 2014, it hosted Supernova 2014J, one of the most important Type Ia supernova ever studied. And fourth, as a prototype for starburst galaxies, M82 helps astronomers understand what happens when galaxies interact and trigger explosive star formation, a process that was common in the early universe. In this documentary, we'll explore every facet of the Cigar Galaxy, from its discovery in the 18th century to the latest Hubble and Chandra observations. From the furious star formation consuming its gas to the superwind blasting material into intergalactic space. This is the complete story of one of the most violent galaxies in our cosmic backyard.
The story begins on December 31st, 1774. German astronomer Johann Elert Bode was scanning the skies from Berlin when he discovered a faint, elongated nebula near the brighter spiral galaxy M81 in the constellation Ursa Major. He cataloged it as simply another nebulous patch, unaware of its true nature. This object would later become known as Messier 82, though Messier himself didn't discover it. He added it to his catalog based on Bode's observations. 7 years later, in 1781, Charles Messier was finalizing his famous catalog of nebulous objects to help comet hunters avoid confusion. He included both of Bode's discoveries, the brighter spiral as M81 and the fainter, elongated companion as M82. Little did he know that this faint smudge would one day become one of the most studied galaxies in the sky. For nearly 2 centuries, M82 remained a curiosity, just another faint nebula in Messier's catalog. But in the mid-20th century, as telescopes improved, its true nature began to emerge. Radio observations revealed intense hydrogen emission, hinting at energetic processes. In 1963, astronomers Linz and Sandage published a landmark study showing that M82 was expelling vast amounts of gas from its center, the first evidence of a galactic superwind. The Cigar Galaxy was finally revealing its explosive personality. Let's establish where we are. The Cigar Galaxy lies at a distance of approximately 12 million light-years from Earth. It's part of the M81 group, a collection of about 34 galaxies that includes its larger neighbor, the Grand Design Spiral M81. At this distance, M82 is one of the closest starburst galaxies to us, which is why we can study it in such exquisite detail. Its light left the galaxy when our ancestors were just beginning to develop agriculture, a relatively short time in cosmic terms. In terms of size, The Cigar Galaxy spans about 37,000 light-years in length when viewed edge-on, but its disk is only about 5,000 light-years thick. That's what gives it that distinctive cigar shape. We're seeing it nearly edge-on, so its disk appears elongated. By comparison, the Milky Way is about 100,000 light-years across, making M82 roughly one-third the size of our galaxy. Its mass is about 10 billion solar masses, an order of magnitude less than the Milky Way's. The Cigar Galaxy's classification is somewhat ambiguous. It's often listed as Type I0, meaning an irregular galaxy with peculiar features. However, some astronomers classify it as an S0 lenticular galaxy, a disk galaxy without prominent spiral arms that has been heavily disrupted by interactions. The truth is, M82 is so distorted by its encounter with M81 that it doesn't fit neatly into any standard classification. Its chaotic appearance is a direct result of its violent history. The Cigar Galaxy is moving away from us at about 203 kilometers per second, based on its redshift. But more importantly, it's moving relative to its companion M81. The two galaxies are separated by only about 150,000. About 100 million years ago, the Cigar Galaxy had a close encounter with its larger neighbor, the spiral galaxy M81. The gravitational interaction between the two galaxies sent shockwaves through M82's disk, compressing clouds of gas and triggering a cascade of star formation. Unlike a full merger, this was a flyby event. The galaxies passed close enough to affect each other but didn't merge. The effects, however, have been dramatic and long-lasting. The starburst was likely triggered by interaction with neighboring galaxy M81 about 100 million years ago. The starburst activity isn't spread evenly across the galaxy. It's concentrated in the central 1,000 light-years. In this relatively small region, massive star clusters are forming at an incredible rate. The most massive of these clusters contain hundreds of thousands of stars, many of them hot, short-lived, and destined to end their lives in spectacular supernova explosions. This central region is so crowded with stars that the radiation pressure and stellar winds have carved out bubbles and cavities in the surrounding gas. The stars forming in M82 starburst are not like our Sun. They're mostly massive O-type and B-type stars. Stars 10 to 100 times more massive than the Sun, burning hot and fast. These stars have lifespans measured in millions rather than billions of years. They produce intense ultraviolet radiation, ionizing the surrounding gas and creating the bright nebulae we see in images. And when they die, they do so catastrophically, as supernovae. Starbursts can't last forever. The Cigar Galaxy has been in its current phase of intense star formation for about 100 million years, and it has enough gas left to continue for perhaps another 100 million years. After that, the gas will be depleted, either converted into stars or blown out of the galaxy by the superwind. The starburst will fade, and M82 will settle into a quieter existence, its glory days behind it. We're witnessing the galaxy at a special moment in its history.
What if we could see space-time? Not just imagine it in equations, not just trace it in diagrams, but see it, feel it, move through it. What would it look like? How would it behave? What secrets would it reveal? This is not a documentary about physics. This is more than just physics. This is an experience, a journey into the fabric of reality itself. We are all swimming in an ocean we cannot see. Every moment of our lives, we move through space-time. We are carried by it, shaped by it, bound by it. But we cannot perceive it directly. It is invisible, like a fish that cannot see the water it swims in. But what if we could? What if we could open our eyes to the fabric of reality itself? In this documentary, we will open those eyes. We will visualize space-time as it truly is. A dynamic, flowing, living fabric that bends around every particle of matter, that ripples with every cosmic collision, that carries us through the universe at the speed of light. We will see it around a star, around a black hole, around your own body. This is general relativity, made visible. For centuries, we saw the universe through Isaac Newton's eyes. Space was a vast, empty stage, fixed, absolute, unchanging. Time was a universal clock, ticking the same for everyone, everywhere. If you moved through space. Time just passed. Simple, intuitive, wrong. Absolute space in its own nature remains always similar and immovable. In Newton's universe, space was a rigid grid. You could travel anywhere,
and the grid stayed the same. Time was a river flowing at a constant speed. Nothing could change them. This was the world we knew for 200 years. Then a young patent clerk in Switzerland had an idea that would shatter it. The cracks in Newton's universe appeared in the 19th century. Scientists noticed something strange. The speed of light seemed to be constant, no matter how fast you were moving. That shouldn't happen. If you shine a light from a moving train, shouldn't it go faster? It didn't. Something was wrong. Something was missing. Something was about to change everything. In 1905, a 26-year-old Albert Einstein had a thought experiment. What would it be like to ride a beam of light? That question led him to a radical conclusion. The speed of light is constant for all observers. This simple idea had a mind-bending consequence. Time is not absolute. If you move very fast, time slows down for you. Einstein asked, "What would I see if I rode a beam of light?" If you travel at 90% of light speed, time slows by half. At 99.9%, it slows by a factor of 22. At 99.9999%, years on Earth pass like days for you. Time is not a universal river. It is a flexible fabric that can be stretched and compressed by motion. They are inextricably linked. Einstein realized that space and time were not separate. They were woven together into a single, four-dimensional fabric. He called it space-time. Every event in the universe has a location in space-time. 3 coordinates for space, 1 for time. You cannot move through space without moving through time. As Hermann Minkowski said, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve reality. To understand space-time, we use a simple analogy. Imagine a rubber sheet. Place a heavy ball on it. The sheet dips. That dip is gravity. A smaller ball rolls toward the larger one not because it's being pulled, but because it's simply following the curve of the sheet. Gravity is geometry. Einstein summarized it. Matter tells space-time how to curve. Space-time tells matter how to move. This is the essence of his vision. But space-time is not a 2D sheet. It is a 3D fabric that wraps around everything. A massive star creates a 3D warp in the space around it, and that warp is what we feel as gravity. If we could see space-time, this is what we would see. A star is not a point of light in empty space. It is a weight on the fabric of reality, bending it, warping it. And everything around it, planets, comets, light itself, is simply following those curves. Exploring the impossible, one curve at a time. Some questions seem too big to answer. We answer them anyway. Join us as we unravel the mysteries of the universe.
Earth is not just a rock floating in space. It is a dent in the fabric of reality, a warp in space-time, and you are inside that warp. The sun's warp is enormous. Planets don't orbit because of a mysterious force. They are simply rolling along the curve of space-time like marbles in a funnel. If you could see space-time, you'd see that time is not uniform. Near massive objects, the fabric is stretched, and time itself flows slower. It's a fact. A clock at sea level ticks slower than one on a mountain. Your head is actually slightly older than your feet. Now imagine a neutron star. Its warp is so extreme that time passes at half the rate. 1 year, there is 2 years elsewhere in the universe. Time dilation is not just science fiction. It is a fundamental fact of our universe. If we could see space-time, we would see it happening everywhere.
Some questions seem too big to answer. We answer them anyway. If we could see space-time around Earth, we would see something surprising. It is not uniform. Earth's gravity varies from place to place. Mountains create tiny warps. Ocean trenches create dips. The geoid, the shape of Earth's gravitational field, is a lumpy, uneven landscape of space-time. Every satellite in orbit is navigating this warp. They follow the curves like marbles rolling in a bowl. The orbits are not circles or ellipses in empty space. They are paths through curved space-time. GPS satellites have to account for both the warp of Earth and the time dilation of their motion. Earth's rotation does something even more subtle. It drags space-time with it. This is called frame dragging. As Earth spins, it twists the fabric of space-time around it, like stirring honey with a spoon. This effect has been measured by satellites. If we could see space-time, we would see Earth's warp slowly rotating. Now we come to the ultimate warp, a black hole. Here, space-time is stretched to its limit. Near the event horizon, the fabric is falling inward faster than light itself. Light can travel outward at the speed of light, but the fabric is moving inward even faster. So light cannot escape. The event horizon is the point of no return. Space-time is falling into the black hole faster than light. That's why nothing can escape. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. What you see is not the black hole itself, it is the silhouette of space-time warped beyond return. The glowing ring is light from matter heated to billions of degrees. This is what space-time looks like at its most extreme. If you fell toward a black hole, you would experience the ultimate expression of space-time curvature, spaghettification. The gravity at your feet would be much stronger than at your head. You would be stretched into a long, thin strand of matter. This is not a metaphor. This is what happens when space-time is stretched to its breaking point. Inside the event horizon, space-time becomes something else entirely. Time and space swap roles. What was space becomes time. What was time becomes space. The singularity at the center is where space-time ends, where our understanding ends, where the universe hides its deepest secrets.
If space-time is a fabric, then violent events should create ripples, gravitational waves. In 2015, scientists at LIGO detected these ripples for the first time. From two black holes merging 1.3 billion light-years away, if we could see space-time, we would see these waves passing through us constantly. LIGO scientists stated, "We have detected gravitational waves. We did it. Every moment, the fabric of space-time is being stretched and compressed by distant cosmic collisions. These waves are passing through you right now. The effect is tiny, smaller than a proton, but it is real. When two black holes merge, they release more energy in a fraction of a second than all the stars in the universe combined. That energy is not light, it is waves in space-time itself. They stretch and compress space as they pass." In the GW1 Fanvo 914 event, 3 solar masses were converted entirely into gravitational waves. If we could see space-time, we would see these ripples as clearly as waves on an ocean. The effect on Earth is smaller than a proton, but it means the universe is breathing. If we could see space-time on the largest scale, we would see the cosmic web. The distribution of galaxies is not random. They cluster along filaments of dark matter, and those filaments warp space-time. The universe is not a flat, empty void. It is a complex, curved landscape of peaks and valleys, hundreds of millions of light-years across. Our own local group is being pulled toward a region called the Great Attractor. Something massive is warping space-time. Galaxies are flowing toward it like water down a drain. We cannot see it directly, but its warp is unmistakable. On the largest scale, the shape of space-time determines our fate. Is it flat, like a sheet? Is it positively curved, like a sphere, where traveling in a straight line brings you back? Or is it negatively curved, like a saddle? Measurements show it is nearly flat, but the answer is not yet certain. Some questions seem too big to answer. We answer them anyway.
At the smallest scales, the Planck scale, a trillion times smaller than a proton, space-time is not smooth. It is a frothing, bubbling foam. Quantum fluctuations constantly create and destroy tiny bubbles of space-time. This is the quantum foam. If we could see space-time at this scale, we would see a universe in constant flux. The scales here are unimaginable. The Planck length, 1.6, is 10 to 35 meters. It is the smallest possible unit of distance. And Planck time, 5.4 x 10^44 seconds, the smallest tick of the cosmic clock. Beyond this, physics breaks down. This bubbling foundation is where space and time itself are born. In this foam, particles pop into existence and vanish. They borrow energy from space-time itself, then return it. This is not empty space. It is the seething, boiling foundation of reality, and we are made from it. If space-time is a four-dimensional fabric, why does time feel different from space? Why can we move left and right but not backward in time? This is the arrow of time. And it is one of the deepest mysteries in physics, why the past is gone and the future is yet to come. The arrow of time comes from thermodynamics, the flow of heat, the increase of disorder. In the beginning, the universe was highly ordered. Since then, it has been unwinding. That unwinding is what we experience as time. The arrow of time is the memory of the Big Bang. If you could see space-time from outside, you would see a human life as a single continuous line, a world line. Every moment of your existence from birth to death is already there in the fabric. We experience it one moment at a time, but in space-time, it is all there, all at once. Some questions seem too big to answer. We answer them anyway. Follow for more.
We have journeyed through space-time, from the smallest quantum foam to the largest cosmic web. We have seen the fabric that holds everything together. We have seen it warp around stars. We have seen it ripple with gravitational waves. We have seen it tear around black holes. We have seen where it ends. The fabric is still there, invisible as always, but now we know it. We have seen it. And now we return to Earth, to a person looking up at the stars. It is not empty space. It is not separate from us. It is the medium we move through, the medium we are made of. We are not in space-time. We are part of it. As Einstein once said, the distinction between past, present, and future is only a stubbornly persistent illusion. The next time you look at the stars, remember, you are not looking through empty space. You are looking through the fabric of reality itself. It bends around you. It flows through you. You are made of it, and you are part of it. This is space-time. This is the universe. This is where you live. You are here. You are part of this fabric. Thank you for joining us on this journey through space-time. If it changed your perspective, share it with someone who needs to see the fabric of reality. Comment below. What would you want to see if you could look at space-time? Some questions seem too big to answer. We answer them anyway.
What if space is not a vast, empty stage stretching endlessly in every direction, but something far stranger? For centuries, we have imagined space as a giant container holding stars, galaxies, and everything we know. It feels solid in concept, measurable in distance, and predictable in motion. Yet modern physics has begun to question this comfortable assumption. Some theories suggest that space may not be fundamental at all. Instead, it could be an emergent property, something that arises from deeper, invisible processes. If that is true, then our understanding of reality may be incomplete at its very foundation. In everyday life, space feels obvious and undeniable. You can walk across a room, measure the distance between cities, or observe the separation between planets. Classical physics, especially Isaac Newton's framework, treated space as absolute and unchanging. It was the grand backdrop against which all events unfolded. However, as scientific understanding advanced, this simple picture began to crack. Observations of light, gravity, and motion at extreme scales revealed inconsistencies. The deeper scientists looked into the universe, the more they realized that space might not be as solid or independent as once believed. Albert Einstein revolutionized our perception of space with his theory of relativity. He proposed that space and time are woven together into a single fabric known as spacetime. Massive objects like stars and planets bend this fabric, creating what we perceive as gravity. Suddenly, space was no longer a rigid container, but a flexible, dynamic entity. It could stretch, curve, and ripple. This insight alone challenged centuries of thought. Yet even Einstein's model may not represent the final layer of reality. Modern physicists now suspect that space-time itself might not be fundamental. Quantum mechanics adds another layer of mystery. At extremely small scales, particles behave in ways that defy common sense. They can exist in multiple states at once and influence each other instantly across vast distances through quantum entanglement. These behaviors suggest that the underlying structure of reality is not built upon smooth, continuous space. Instead, it might arise from probabilistic interactions at a deeper level. If quantum processes generate what we perceive as space, then the emptiness between objects may be more like a projection than a physical expanse. One compelling idea is that space emerges from information. Some physicists argue that the universe at its core is composed not of matter or energy, but of bits of information. According to this view, space is a kind of large-scale illusion formed by patterns of informational relationships. Just as a digital image appears continuous though it is made of pixels, space might seem smooth while being constructed from discrete elements. If this theory is correct, then the distances we measure are manifestations of underlying informational structures. If this theory is correct, then the distances we measure are not fundamental realities, but manifestations of underlying informational structures. The holographic principle offers another radical perspective. It proposes that all the information contained within a volume of space may actually be encoded on its boundary. In simple terms, our three-dimensional universe could be a projection of information stored on a distant two-dimensional surface. This idea arose from studying black holes and their entropy. While it sounds like science fiction, mathematical models support its plausibility. If the holographic principle is true, then space as we experience it may not be the ultimate layer of existence. If the holographic principle is true, then space as we experience it may not be the ultimate layer of existence. Black holes play a crucial role in this discussion. When matter falls into a black hole, information about it seems to be preserved at the event horizon. This paradox challenged physicists for decades. To resolve it, researchers explored the possibility that space-time itself is encoded in more fundamental degrees of freedom. In this scenario, space is not a stage, but a network of connections. Break those connections, and space itself might dissolve. In this scenario, space is not a stage, but a network of connections. Break those connections, and space itself might dissolve. Another fascinating concept comes from quantum gravity research. Scientists attempting to unify general relativity with quantum mechanics have proposed that space-time might be granular. Instead of being infinitely divisible, it could consist of tiny, discrete units at the Planck scale. These units would be unimaginably small, far beyond current experimental reach. If space-time is quantized, then smooth space is merely an approximation at large scales. What we perceive as continuous extension may actually arise from countless microscopic building blocks. What we perceive as continuous extension may actually arise from countless microscopic building blocks interacting beneath perception. Loop quantum gravity is one approach exploring this possibility. It suggests that space is made of finite loops woven into an intricate network. These loops form a structure called a spin network, which defines the geometry of space. Rather than existing within space, these networks create space itself. If accurate, this model implies that without these fundamental connections, there would be no distance or direction at all. Space would not disappear. Rather, it would never have existed independently. Space would not disappear. Rather, it would never have existed independently in the first place. string theory offers a different but equally intriguing perspective. It proposes that the fundamental constituents of reality are tiny vibrating strings. In some versions of the theory, space emerges from the interactions of these strings. The geometry we observe could be shaped by how these strings vibrate and connect. Though still unproven, string theory hints that space might not be the ultimate container, but a dynamic outcome of deeper physical processes. Though still unproven, string theory hints that space might not be the ultimate container, but a dynamic outcome of deeper physical processes occurring in dimensions beyond our direct perception. Quantum entanglement provides some of the strongest clues that space might be secondary. When two particles become entangled, they remain connected regardless of distance. Measurements performed on one instantly affect the other, even if they are light years apart. This phenomenon challenges the classical notion of space as a barrier. Some researchers propose that entanglement itself constructs space-time geometry. In this view, spatial separation is not fundamental but derived from patterns of entangled relationships. Distance may simply measure how strongly systems are connected at a quantum level. Recent theoretical work suggests that space-time could emerge from quantum error-correcting codes. These mathematical frameworks describe how information can be protected from corruption. Surprisingly, certain models show that geometric properties resembling space-time naturally arise from informational stability. This implies that space might be a byproduct of how quantum information organizes itself. Rather than being a pre-existing arena, space could be the outcome of complex computational principles operating at the universe's deepest scale. Rather than being a pre-existing arena, space could be the outcome of complex computational principles operating at the universe's deepest scale. If space is emergent, then our perception of movement also changes. Motion would not involve traveling through a pre-existing medium, but shifting relationships. Just as moving through a digital map changes coordinates without altering the underlying hardware, physical motion might represent reconfigurations in informational patterns. This interpretation reframes reality as dynamic computation rather than static extension. It challenges intuition but aligns with modern theoretical trends seeking unity between gravity and quantum mechanics. If space itself is born from hidden connections, then the universe is not an empty void but a vast web of relationships, continuously generating the stage upon which existence unfolds.
Imagine a volcano so massive that it would cover the entire state of Arizona, so tall that its summit would be 3 times higher than Mount Everest, so wide that its base stretches 600 kilometers across the Martian landscape. This is Olympus Mons, the largest volcano in the solar system. A shield volcano of such immense scale that it defies terrestrial comparison. Located in the Tharsis region of Mars, this giant has been extinct for millions of years. But its features tell a story of volcanic activity that shaped the red planet and holds clues to Mars's watery past. This is the story of Olympus Mons, the giant that towers over Mars. Why does it matter to planetary scientists? Because it represents a volcanic end member, the extreme of what shield volcanoes can become. Its low gravity, stable crust, and long-term hotspot activity allowed it to grow to impossible proportions. But beyond its size, Olympus Mons holds mysteries, the steep cliffs at its base and the surrounding aureole deposits, and the possible role of water in shaping its unique features. Understanding Olympus Mons helps us understand Mars itself. NASA states, with a base that sprawls across 373 miles, the shield volcano rises to a height of 17 miles. In this documentary, we'll explore every facet of Olympus Mons, from its staggering dimensions to its volcanic origins. This is the complete story of the solar system's largest volcano. let's begin our journey. Let's start with the most staggering number, height. Olympus Mons stands 27 kilometers above the surrounding Martian plains. To put that in perspective, Mount Everest is just 8.8 kilometers above sea level. You could stack 3 Mount Everests on top of each other and still not reach the summit of Olympus Mons. Its peak rises so high that it actually extends above most of Mars's thin atmosphere. But height is only part of the story. Olympus Mons spans 600 kilometers in diameter, roughly the size of the state of Arizona. Its base is so vast that if you stood at the edge, you couldn't see the summit. It would be hidden below the curvature of the planet. The entire Hawaiian island chain, from the Big Island to Kauai, would fit comfortably within its footprint. The volume is almost incomprehensible. Olympus Mons contains about 100 times more material than Mauna Loa, Earth's largest volcano. Its sheer mass has actually depressed the Martian crust beneath it. The volcano is so heavy that it has created a flexural trough surrounding the entire edifice. Unlike the steep cones of stratovolcanoes, Olympus Mons is a shield volcano with remarkably gentle slopes. The central part rises at an angle of only 1 to 5 degrees, so gradual you could walk up without noticing the incline. But at the edges, everything changes. The periphery terminates in steep cliffs that slope 12 to 28 degrees, dropping 8 kilometers to the plains below. Olympus Mons is a shield volcano formed by the eruption of low-viscosity basaltic lava. Unlike thick, sticky lava that builds steep cones, this fluid lava spreads out in thin layers, creating a broad, gently sloping profile. Over millions of years, layer upon layer stacked up to create the massive edifice we see today. Eruption rates were similar to those observed in terrestrial hotspot volcanism. Olympus Mons likely formed over a long-lived hotspot, a plume of hot material rising from deep within Mars's mantle. Unlike Earth's moving plates, Mars's thick, immobile crust allowed the volcano to remain stationary. This is why it grew so large. It never moved away from its magma source, feeding from the same hotspot for billions of years. Mars' gravity is only 38% of Earth's. This lower gravity means that lava can build higher structures without collapsing under their own weight. On Mars, the reduced gravity allowed Olympus Mons to reach heights that would be impossible on our planet. Gravity simply doesn't pull it down as strongly. Building something this massive takes time. Geological evidence suggests that the main construction phase lasted approximately 1.1 billion years, from about 3.67 to 2.54 billion years ago. During this period, lava erupted at a rate comparable to Earth's hotspot volcanism. Activity later dropped off, though low-level eruptions may have continued for hundreds of millions of years. A stationary hotspot, low gravity, and over 1 billion years of steady eruptions. This is how Mars built the solar system's greatest giant.
Look up. On any given night, you might see it, a silent, glowing orb, our closest cosmic neighbor. For all of human history, the moon has been our companion, a source of light in the darkness, a keeper of time, and a canvas for our myths and dreams. But what is it really? This is the story of our moon. 250,000 miles away, that's about 30 Earths placed end to end, it orbits us. It's a world of stark contrasts. About a quarter the size of Earth, its gravity is just 1/6 of what you feel here. A place where daytime temperatures soar higher than boiling water, and nights plunge to -280 degrees Fahrenheit. A silent, airless, and lifeless world. And yet, it doesn't always look the same. Its beautiful, predictable dance through the sky gives us the phases. As it orbits us, the sun illuminates different parts of its face. From a slender crescent, a symbol of new beginnings, to the awe-inspiring full disk of the hunter's moon. This celestial ballet has been humanity's first clock, marking the passage of months and seasons. But the moon we see today wasn't always there. Ancient cultures told stories of its birth. But the true origin is a tale more violent and spectacular than any myth. It's a story of a cosmic catastrophe that happened over 4.5 billion years ago. Meet Theia, a rocky protoplanet from the early solar system. In a chaotic cosmic shooting gallery, its path crossed with that of the young Earth. The result wasn't a simple crash. It was a titanic glancing blow that vaporized Theia and a huge chunk of Earth's mantle, sending a cloud of molten rock and gas spinning out into space. For thousands of years, Earth wore a ring, but gravity is persistent. This massive disk of debris began to coalesce, pulling itself together piece by piece. In a cosmic blink of an eye, the material clumped into one object. Our moon was born. And in its infancy, it was incredibly close, 10 times closer than it is today, filling our skies as a gigantic, terrifying, and beautiful sight. This newborn moon was a ball of molten magma, a world of lava. As it slowly cooled over millions of years, lighter minerals floated to the surface, forming its primordial crust. This infant world was then relentlessly pummeled by leftover debris from the solar system's formation, a violent bombardment that would forever scar its face. This violent birth gave us a gift. The moon's powerful gravity pulls on our planet, creating the tides. As the moon orbits, it drags Earth's oceans with it, creating the rhythmic pulse of the seas. This daily ebb and flow may have been the perfect mixing pot for the complex chemistry of life, helping to move from the oceans onto land. When you look at the moon, you're seeing two different stories written on its face. The dark, smooth patches are called Maria, Latin for seas. Early astronomers mistook them for actual oceans. We now know they are vast, ancient lava plains. The brighter, heavily cratered regions are the lunar highlands, the original ancient crust. The Maria were born from violence. After the initial bombardment, giant asteroids smashed into the moon, creating enormous, deep basins. For millions of years afterward, magma from deep inside the moon pushed up through these weakened crustal cracks, flooding the basins and freezing into the dark, iron-rich rock we see today as the Man in the Moon. Look closely at the full moon. You'll see a bright, almost blinding crater near the bottom. That's Tycho. Its rays are streams of ejected material blasted out by a relatively recent impact, only 108 million years ago. And craters like Copernicus, with their magnificent terraced walls and central peaks, show us the incredible power of these impacts, forcing the lunar crust to rebound like a splash in a pond. But up close, the moon isn't rocky. It's covered in a layer of gray, dusty debris called regolith. For billions of years, micrometeorites, tiny specks of space dust, have been sandblasting the lunar surface at high speed. This constant pounding has ground the rocks into a fine, sticky, and abrasive powder that clings to everything, a layer that perfectly preserves every footprint for millions of years. For millennia, we could only look and wonder. But in the 20th century, the moon became a destination. The Cold War's space race turned our gaze into a goal. First, robotic scouts were sent. In 1959, a Soviet spacecraft captured the first blurry images of the mysterious lunar far side, a hemisphere we never see from Earth. This set the stage for an audacious challenge. The Apollo missions were humanity's greatest adventure, a towering Saturn V rocket, more powerful than anything built before or since, hurled 3 men towards another world. After 3 days of travel, they entered lunar orbit. Then came the moment of truth. The lunar module, a fragile spider of a spacecraft, separated and began its powered descent to the surface. On July 20th, 1969, the world held its breath. The Eagle has landed. Then a ghostly figure descended a ladder and spoke words that will echo for eternity. That's one small step for a man, one giant leap for mankind. For the first time, a being from Earth stood on the surface of another world. Over 6 successful landings, 12 humans walked on the moon. They drove dune buggies across its plains, set up laser reflectors we still use today, and brought back 842 pounds of moon rock. Priceless geological treasures that continue to teach us about the origins of our solar system. And then, in 1972, we left. And for over 50 years, the moon has been silent, waiting for our return. But we are going back, not just to visit this time, but to stay. NASA's Artemis program aims to land the first woman and the first person of color on the moon. This time, we're building a space station called Gateway in lunar orbit, a pit stop for a new era of exploration. We will build habitats, learn to live off the land. We'll drill for water ice, the key to survival, which can be turned into drinking water, breathable oxygen, and even rocket fuel. The moon will become our proving ground, a harsh but perfect test bed for learning how to live on another world. From a mysterious light in our sky to a world we've touched, to a future home. Our moon is more than just a rock. It's a time capsule, a cosmic mirror, and our first step towards the stars. The journey that began with a look up is far from over. It's only just beginning.
Getting to the moon looks easy on paper. Just point a rocket at it and go. Right? Wrong.
Every meter of that 400-kilometer journey is a battle against forces that want you dead. From the moment of launch to the moment of landing, 1,000 things can go wrong, and most of them have. The moon has killed spacecraft before. It's killed astronauts in simulations. It's come terrifyingly close to killing them in real missions. This is the story of what it really takes to get a spaceship to the moon, and why it's the hardest thing humanity has ever attempted. Why is getting to the moon so incredibly difficult? Because you're fighting against everything. Gravity wants to pull you back. The vacuum of space wants to crush you from the inside. Radiation wants to cook you. Temperature swings of 300 degrees want to destroy your equipment. And the moon itself, that beautiful, silent world, is covered in razor-sharp dust that wants to tear your spacesuit apart. Every mission is a war against physics itself. The stakes couldn't be higher. In 1967, 3 astronauts died in a fire on the launch pad, killed not in space, but during a simple test. Apollo 13 came within minutes of losing its crew to an explosion 200,000 miles from home. Every astronaut who straps into a rocket knows the statistics. They know that spaceflight is, and always will be, incredibly dangerous. But they go anyway, because some things are worth the risk. In this documentary, we'll follow a spacecraft on its impossible journey to the moon. From the terror of launch to the violence of booster separation. From the silent emptiness of space to the invisible threat of radiation. From the critical engine burns to the nail-biting landing. We'll explore every challenge, every danger, every moment where one mistake means death. It starts here. On a launch pad in Florida, 1 million kilograms of metal and fuel stand ready. The astronauts have said goodbye to their families. They've been strapped into their seats for hours. Below them, 8.8 million pounds of thrust wait to be unleashed. The moment of ignition is pure violence. The engines consume 15 tons of fuel per second. The sound is indescribable, so loud it can kill you if you're too close. The vibration shakes the very ground. And yet, inside the capsule, the astronauts feel surprisingly little. Just a gentle push, then acceleration. About a minute into flight, the rocket hits max Q, maximum dynamic pressure. The atmosphere is still thick, but the speed is enormous. The forces on the vehicle are higher than at any other point in flight. One weld too weak, one material flaw, and the rocket could tear itself apart. 2 minutes in, the solid rocket boosters have done their job. Explosive bolts fire, and the boosters fall away. They'll parachute into the Atlantic to be recovered. The core stage pushes on, its engine still burning. 8 minutes after launch, the core stage has done its job. Empty of fuel, it separates and falls back to Earth. The upper stage takes over, pushing the spacecraft into a parking orbit around Earth. For the first time, silence. They've made it to space. But what if something goes wrong? Every crewed spacecraft has a launch abort system. A small rocket on top of the capsule that can fire, pulling the crew away from a failing booster in milliseconds. The spacecraft has reached Earth orbit, about 200 kilometers up, circling the planet every 90 minutes. This is the first checkpoint. From here, they could still turn back if something's wrong. But everything checks out. Mission Control gives the go. For the next few hours, the crew runs through an exhaustive checklist. Every system is tested, every reading is verified. The engineers on the ground analyze telemetry, looking for anything out of the ordinary. But everything is perfect. Their go for translunar injection. Through the window, Earth is beautiful, more beautiful than any photo can capture. The astronauts know this might be their last view of home for a while. In a few hours, they'll fire the engine that sends them toward the moon. It's a moment of profound emotion for every human who's ever left Earth orbit. Now comes the most critical burn of the mission, translunar injection. The upper stage fires for about 5 minutes, adding enough velocity to escape Earth's gravity and head toward the moon. The acceleration pushes the crew back into their seats. Outside the window, Earth begins to shrink. When the burn is complete, they're on a trajectory that will take them 250,000 miles from home. The precision required for this burn is almost incomprehensible. The engine must fire for exactly the right duration, at exactly the right angle. If it's off by a fraction of a second, they'll miss the moon entirely, either swinging past into deep space or crashing into the surface. The navigation computers calculate every variable, and the crew monitors every reading. One mistake, and they're lost forever. When the engine cuts off, silence returns. The only sounds are the hum of fans and the occasional crackle of the radio. Earth is already visibly smaller, shrinking by the hour. The astronauts are now farther from home than any humans in history. Once they leave Earth's protective magnetic field, the crew enters a dangerous environment: deep space radiation. Cosmic rays from distant supernovae, solar particles from our own sun, they constantly bombard the spacecraft. On Earth, we're protected. Here, there's nothing. Just a few millimeters of aluminum between the crew and cancer-causing radiation. Before they even leave Earth's neighborhood, the spacecraft must pass through the Van Allen belts, 2 regions of trapped radiation that can be deadly. The biggest radiation danger isn't the constant background, it's the unpredictable. Solar flares can erupt without warning. Modern missions include a storm shelter, a small heavily shielded compartment where the crew can wait out a flare. In deep space, temperature is a constant battle. In direct sunlight, the spacecraft can reach 120 degrees Celsius. In shadow, it can drop to -150. Space isn't empty. It's filled with tiny particles, micrometeoroids, moving at incredible speeds. A grain of sand can carry the energy of a bullet. Beyond the physical dangers, there's the psychological challenge, the isolation, the knowledge that no one can rescue you. They're alone out here, farther from home than anyone in history, and they have to be okay with that. Before they can land, they have to lower their orbit. Another engine burn, another critical maneuver. The landing site comes into view. For Artemis missions, it's near the lunar South Pole where ice lurks in permanent shadow. Now comes powered descent initiation. The lander fires its engines to slow down and begin the drop to the surface. From here, everything is automatic, but the crew monitors every reading, ready to abort. The surface is still 15 kilometers below, rushing up. Landing on the moon is incredibly difficult. Modern landers use terrain relative navigation, cameras that image the surface and identify safe sites. In the final seconds, something dangerous happens. The engine blast kicks up lunar dust. It can blind the cameras and confuse the sensors. Then, touchdown. Probes on the landing legs sense contact. The engine cuts off. Dust settles. Silence returns. For a moment, no one moves. Then the checks begin. Systems nominal. They've done it. They're on the moon. The impossible journey is complete. They've landed. But the challenges aren't over. They've just changed. The lunar surface is one of the most hostile environments in the solar system. No atmosphere means no protection from radiation. Temperature swings of 300 degrees between day and night. And everywhere, there's dust. Lunar dust is unlike anything on Earth. Formed by billions of years of micrometeorite impacts, it's microscopic, razor-sharp, and electrostatically charged. It sticks to everything. On Apollo missions, it wore through spacesuit gloves, clogged equipment, and even caused lunar hay fever in astronauts. Lunar dust is not just a nuisance. It's one of the biggest technical and safety challenges for future moon missions. It's sharp, sticky, and potentially harmful. Why is lunar dust so sticky? Radiation from the sun gives it an electrostatic charge. This causes them to levitate and stick to anything with an opposite charge. Spacesuits on the moon face an impossible task. They have to maintain Earth normal pressure in a vacuum. They have to allow movement despite that pressure. They have to protect against radiation and micrometeoroids, and they have to keep out dust that's sharp enough to cut through fabric. Engineers are working on solutions. One promising technology uses carbon nanotubes woven into spacesuit fabric to create a field that repels charged dust particles. NASA's Artemis program isn't just about visiting the moon, it's about staying. Future missions will establish a lunar base. They'll learn to use local resources and prepare for Mars. But that means solving new challenges, long-duration life support, and radiation protection. The Gateway will be a space station in lunar orbit, a home base for astronauts, a laboratory for science, and a staging point. It solves some problems while creating others. How to maintain mental health and physical safety while living far from Earth for months. The key to sustainable presence is living off the land. The moon has water ice at its poles, enough to drink and make rocket fuel. In situ resource utilization, ISRU, is the technology that will turn lunar ice into oxygen and hydrogen. Future missions won't bring all their fuel from Earth. Everything we learn on the moon prepares us for Mars. The same challenges, radiation, dust, life support, will be magnified 100-fold. The moon is our training ground, our test bed, our first step toward becoming a multi-planetary species. The challenges we overcome here make everything else possible. Getting a spaceship to the moon is the hardest thing humanity has ever done. The challenges are endless, the risks are real. But we've done it. We've done it before. And we're doing it again. We look at the impossible, and we figure out how to make it possible. We can't forget the cost. Brave men and women have given their lives in this pursuit. They knew the risks, and they went anyway. Their sacrifice reminds us that exploration isn't just about glory. It's about courage, about believing that some things are worth dying for. The next mission is already being planned. New astronauts are training. The journey to the moon will never be easy, but it will always be worth it. Because when we look up at that silver disk in the sky, we know that humans have walked there, and they will walk there again. The journey to the moon is 384,400 kilometers of terror, but it's also 384,400 kilometers of hope, of courage, of human achievement. Every spacecraft that makes the journey carries the dreams of everyone who's ever.
For centuries, we looked at the stars and wondered, are we alone? Are there other worlds like ours, orbiting distant suns? In 2016, astronomers found the closest possible answer. Just 4.24 light-years from Earth, a stone's throw in cosmic terms, a planet orbits our nearest stellar neighbor. It's called Proxima Centauri b. It's rocky, Earth-sized, and sits in the habitable zone, the region where liquid water could exist. But is it truly another Earth? Or is it something else entirely? This is the story of our closest cosmic neighbor. And the question that haunts astronomers, could we ever call it home? The discovery came from the European Southern Observatory's La Silla facility in Chile. Astronomers were studying Proxima Centauri using the radial velocity method, measuring the tiny wobble in the star's motion. After years of observations, the signal was clear. A planet with at least 1.3 times Earth's mass, orbiting every 11.2 days. That's much closer than Mercury is to our Sun. But because Proxima Centauri is a red dwarf, this places the planet in the habitable zone. The discovery made headlines around the world. For the first time, we knew of an Earth-sized planet orbiting our closest stellar neighbor. To understand Proxima b, you have to understand its sun. Proxima Centauri is a small, cool, and incredibly long-lived star. But it's also temperamental. Red dwarfs are prone to powerful solar flares that release enormous amounts of radiation. Proxima Centauri's flares can be hundreds of times more powerful than our Sun's, and Proxima b feels their full fury. This single fact may determine whether the planet is a potential second Earth or a radiation-blasted wasteland. In this documentary, we'll explore every aspect of Proxima Centauri b, from the science of its discovery to the dream of sending humans there. From the brutal challenges of its environment to the solutions for survival, we'll imagine the 100-year journey, the first footsteps, and the birth of a new branch of humanity. This is Proxima b, 4.24 light-years. It sounds almost close, just 4 years at the speed of light. But light-years are deceptive. 1 light-year is 9.46 trillion kilometers. Multiply that by 4.24 and you get 40 trillion kilometers. 40,000 kilometers. To put that in perspective, the distance from Earth to Pluto is just 5 billion kilometers. The Voyager spacecraft would take over 70,000 years to reach Proxima b at their current speed. The distance defies human comprehension. With current technology, reaching Proxima b is impossible. The fastest spacecraft we've ever built, the Parker Solar Probe, would still take 6,300 years. That's longer than recorded human history. To reach Proxima b in a human lifetime, we need breakthroughs, nuclear fusion, or light sails pushed by lasers. We need something we haven't even imagined yet. Breakthroughs that transform our understanding of the possible. One proposed solution is the Generation Ship, a spacecraft so large that multiple generations can live and die during the journey. The Helianthus, as envisioned, carries 4,752 colonists on a 100-year voyage. 7 generations are born, live, and die on board. They know only the ship, the recycled air, the artificial gravity, the same faces day after day. Their descendants will be the ones to finally step onto an alien world. It raises profound questions. Would those born during the journey feel privileged to be part of humanity's greatest adventure? Or resentful of a destiny they never chose? A life confined to a hull of steel and glass, 40 trillion kilometers from home. A 100-year journey presents another challenge: genetic diversity. With only a few thousand settlers, maintaining a healthy gene pool requires careful planning. Genetic counseling becomes mandatory. Gene editing might be necessary to eliminate hereditary diseases. Every life is a building block for the future. Cryogenically stored genetic material from Earth could introduce new traits long after departure. The Helianthus carries the entire genetic future of a new branch of humanity. They are the bridge across the void, the pioneers of the great emptiness, carrying the spark of Earth into the deep unknown. Let's look at what we actually know about Proxima Centauri b. It has at least 1.3 times Earth's mass, making it a rocky super-Earth or mini-Neptune. It orbits its star in just 11.2 Earth days. Its orbit is incredibly close, just 7.5 million kilometers from the star, compared to Earth's 150 million. But because Proxima Centauri is so much dimmer than our Sun, that close orbit actually places it in the habitable zone, where liquid water could exist. The habitable zone is where surface temperatures could allow liquid water. Around our Sun, it stretches past Mars. Around a red dwarf, it's much closer and narrower. But being in the habitable zone doesn't guarantee habitability. Venus is in our Sun's zone, and it's a hellish pressure cooker. Mars is a frozen desert. History matters. Here's where things get complicated. Because Proxima b orbits so close, it's almost certainly tidally locked. Just like our moon is locked to Earth. One hemisphere perpetually faces the star, the other away. Between them lies a narrow ring, the twilight zone, where the star hangs perpetually on the horizon. If Proxima b is habitable anywhere, it's probably in this narrow band of eternal twilight. Here, the temperature might be just right, but the biggest threat may come from the star itself. Red dwarfs are volatile. They produce flares that release more radiation in minutes than our Sun does in hours. Proxima's flares can be hundreds of times more intense than our Sun's. Orbiting so close, Proxima b is directly in the firing line. These flares could strip away any atmosphere, bombard the surface with deadly radiation, and make life, as we know it, impossible. Some scientists think Proxima b may have lost its atmosphere long ago, leaving it a barren, irradiated rock, barren and silent. There's another problem, the past. When Proxima Centauri was young, it was much hotter and brighter than it is now. For billions of years, the planet endured extreme conditions. Any water or atmosphere it once had could have been boiled away long ago. Some models suggest Proxima b could be more like Venus than Earth. A hellish world with a thick, toxic atmosphere. A world of secrets. We won't know the truth until we can study it directly. Until then, the mystery remains. Imagine the departure. Thousands of colonists have said goodbye to Earth forever. They've watched their home planet shrink to a dot, then disappear entirely. Ahead lies only emptiness, 100 years of emptiness. The Helianthus accelerates, reaching 4.24% of light speed. Then the engines shut down, and the long coast begins. For the next century, they'll drift through the void, carrying humanity's hopes. Life aboard the Helianthus is carefully structured. The rotating habitat ring generates artificial gravity through centrifugal force. Inside, the ship is a self-contained world. Farms grow food, factories recycle waste, schools educate children who will never see Earth. The population is carefully managed, births planned, genetic diversity maintained, resources rationed. 7 generations will live and die here. The first generation, the ones who actually left Earth, carry memories of home. They remember blue skies and green grass, the smell of rain. But as they age, their numbers dwindle. Their children know only the ship. To them, Earth is a legend, a place in stories. By the time the ship reaches Proxima b, no one on board has ever seen their destination or their origin. The journey has become their home. With only 4,652 initial colonists, genetic diversity is a constant concern. Strict guidelines govern reproduction and matching. Gene editing eliminates hereditary diseases and could eventually enhance resilience to the conditions awaiting them. A carefully managed experiment. 50 years in, the ship is halfway to its destination. No one on board remembers Earth. The stories have become traditions and myths. Some wonder if they'll ever actually arrive, if Proxima b is real, or just a story to give meaning to their existence. But the data says yes. They're on course. In another 50 years, their descendants will see a new sunrise. The journey continues. The destination is calling.
Some questions seem too big to answer. We answer them anyway.
There is a world in our solar system where rain falls from the sky, where rivers carve valleys into the landscape, where vast lakes shimmer under a hazy sky. From a distance, it could be Earth. But this is not Earth. This is Titan, the largest moon of Saturn, and everything about it is alien. The rain is not water, it's methane. The lakes are not filled with water, they're filled with liquid hydrocarbons. The temperature is 179 degrees. And yet, this frozen world may hold the answer to one of humanity's oldest questions. Are we alone? Titan is the only other world known to have stable liquid on its surface. Why Titan? Because Titan has something no other world in our solar system has, except Earth. Stable liquid on its surface. Oceans, lakes, rivers, rain. Not water, but methane and ethane. And where there is liquid, there is the potential for life. Not life as we know it, but life as we never imagined. In this documentary, we'll journey to Titan, the most Earth-like world we've ever found. We'll explore its methane rivers and ethane lakes. We'll dive beneath its icy crust to a hidden ocean of water. And we'll look to the future, to NASA's Dragonfly mission, launching in 2027. This is the story of Titan. Titan is enormous. At 5,150 kilometers across, it's larger than the planet. It's the second largest moon in the solar system. It completes one orbit every 16 Earth days. And it is the only moon in the solar system with a thick atmosphere, 1.5 times denser than Earth's. It's mostly nitrogen, like Earth, methane. That methane is the key. Sunlight breaks it down, creating complex organic molecules that form the orange haze. Titan is an organic factory. Those organic molecules fall to the surface, accumulating over billions of years. If life exists anywhere else in our solar system, Titan is a prime candidate.
In 1997, NASA and the European Space Agency launched the most ambitious mission to the outer solar system ever attempted. Cassini-Huygens would travel 7.9 billion kilometers over 7 years, passing Venus, Earth, and Jupiter, before finally arriving at Saturn in 2004. It was a mission of discovery, and Titan was its primary target. For years, we knew almost nothing about what lay beneath its clouds. That was about to change. On January 14, 2005, the Huygens probe separated from Cassini and began its descent into Titan's atmosphere. For 2 hours and 27 minutes, it fell through the orange haze, taking measurements, sampling the air, and capturing images. No one knew what it would find. No one knew if it would survive. The images were astonishing. From high above, they showed river channels, and then the surface, pebbles of water ice, smoothed by flowing liquid methane. For the first time, we saw another world's surface, shaped by rain and rivers, just like our own. Scientists were stunned to see processes so familiar on a world so alien. Over the next 13 years, Cassini orbited Saturn, flying past Titan 127 times. Its radar pierced the haze, revealing a world of stunning complexity. Hundreds of lakes, some larger than Lake Superior, rivers winding through canyons, dune fields stretching for thousands of kilometers. Titan was not a dead world. It was alive. Titan has a hydrological cycle, but instead of water, it's methane. It mirrors Earth's cycle perfectly. Methane evaporates, forms clouds, falls as rain, flows through rivers, and collects back in the lakes. It is the only world in the solar system, besides Earth, with an active, stable liquid cycle. The largest lake is Kraken Mare. It covers 400,000 square kilometers, about the size of the Caspian Sea. Radar data suggests it is up to 300 meters deep. It is filled with liquid methane and ethane, and its shores are lined with organic material, the building blocks of life. In Ligeia Mare, scientists noticed something strange. Bright features that appeared, then disappeared. They called them magic islands. They might be chunks of organic material, or possibly bubbles of nitrogen gas rising from below. Titan has rivers, long, winding, dendritic, just like on Earth. They carve valleys and transport sediment. Some stretch for hundreds of kilometers, cutting through water ice harder than granite. Near the equator, vast dune fields stretch for thousands of kilometers. They are made of organic particles. These tholins fall from the sky and are piled into dunes by the winds, creating landscapes that look eerily like the deserts of Earth, yet are entirely alien.
As Huygens descended, it revealed a world both alien and familiar. Dark plains stretched to the horizon. Light-colored hills rose in the distance. River channels carved their way across the landscape. The probe was landing in what appeared to be a dry riverbed, a channel that had once carried flowing methane. It's a landscape that looks like Earth. It has hills, it has valleys, It has river channels. It's like something you'd see from a helicopter over Earth. When Huygens landed, it came to rest on a dark plain covered in rounded pebbles. Those pebbles are water ice, harder than granite. They are smoothed by the flow of liquid methane like river rocks on Earth. The surface was damp, the probe sinking slightly into methane-moist soil. Titan is not just a frozen world, it is a world rich in the chemistry that could create life, containing water ice and organic compounds. Deep beneath its icy crust, scientists have discovered something extraordinary, a global ocean of liquid water, 50 to 100 kilometers down. It contains more water than all of Earth's oceans combined. Cassini data has confirmed this global liquid water ocean exists. Cassini measured Titan's rotation and gravity with precision. The moon's rotation was slightly off, suggesting a liquid layer beneath the ice. This ocean has liquid water, organic material, and potential energy sources like hydrothermal vents. The ingredients for life are all there.
On Earth, life requires liquid water, but Titan offers the possibility of a different kind of life, one that survives in liquid methane instead. Scientists propose a radical idea: life that breathes hydrogen and builds its cells from the organic molecules raining from Titan's sky. Intriguingly, Cassini found that hydrogen and acetylene are disappearing from Titan's surface. Could something be consuming them for energy? Researchers have even modeled the azotosome, a theoretical cell membrane made of nitrogen that could make alien life on Titan a reality. In 2027, NASA's Dragonfly mission will launch. This car-sized rotorcraft will fly across Titan to sample its alien landscape. Landing in the Selk crater, Dragonfly will explore where ancient water ice once mixed with organic materials, the perfect place to find life. Equipped with mass spectrometers and cameras, Dragonfly will perform the most comprehensive search for life since the Viking missions. Whatever Dragonfly finds, it will forever change our understanding of life's potential in the universe.
If life exists on Titan, it would be unlike anything on Earth. It would not use water. It would not use oxygen. It would breathe hydrogen and eat acetylene. It would be microscopic, probably living in the lakes or underground. It would be slow, in the deep cold, but it would be alive. It would be a second Genesis. If life doesn't exist on Titan, it will still teach us something profound. It will teach us that the conditions for life are not enough, that something else is required, that we are more unique than we think. Either way, Titan will give us answers. If we find life on Titan, any life, it will be the most important discovery in human history. It will tell us that life is not a fluke. It will tell us that the universe is teeming with it. It will tell us that we are not alone. And it will change everything. For all of human history, we have asked, are we alone? We have looked at the stars and wondered. We have sent probes to the planets and hoped. And now, we are closer than ever to an answer. In 2034, Dragonfly will land on Titan. It will fly across its alien landscape. It will search for the signs of life. The answer may be less than a decade away. By the mid-2030s, we could know. We could know if life exists on another world. We could know if the universe is full of life. We could know if we are alone. Titan is waiting. It has been waiting for 4.5 billion years. And soon, we will go there. We will fly across its lakes. We will touch its surface. We will search for the signs of life. And whatever we find, we will know. We are part of something bigger.
We've journeyed through Titan, a world of methane lakes, organic dunes, and a hidden ocean. We've seen its rivers and rain. We've explored its surface with Huygens. We've mapped its mysteries with Cassini. And we've looked ahead to Dragonfly, which will search for life in the 2030s. Titan is more than just a moon. It is a world with weather, with geology, with chemistry that mirrors Earth's. A world that may hold the key to life. A world that will teach us something about ourselves, no matter what we find. The search for life continues, and Titan is waiting for us to come back, waiting for Dragonfly, waiting to share its secrets. And when we finally land, when we finally fly, we will be taking the next step in the greatest journey humanity has ever undertaken. The journey to find out if we are alone. The journey to find ourselves among the stars. Thank you for joining us on this journey to Titan. If it inspired you, share it with someone who needs to know that we are searching. Comment below. Do you think there is life on Titan?
Elon Musk has a vision, not a colony, not an outpost, a city, 1 million people living on Mars, a self-sustaining civilization, a second home for humanity. It sounds like science fiction, but SpaceX is already building the ships that will take us there. This is the plan. This is how they'll do it. A city on Mars. This is how we become a multi-planetary species. 1 million people. This is the greatest challenge humanity has ever faced. The hardest thing. Elon Musk has been clear about his goal. Not just to visit Mars, to stay, to build a city, to create a self-sustaining civilization that can survive even if Earth is cut off. A backup drive for humanity, a second Genesis, a second home. We need to become a multi-planetary species. Civilization needs a backup drive. In this documentary, we'll explore the complete SpaceX plan for Mars, from the Starship that will take us there to the propellant plant that will bring us home, from the first habitats to the million-person city, from the challenges to the triumphs. This is how SpaceX will build our city on Mars. Why Mars? Because Earth is fragile. A single asteroid, a supervolcano, a nuclear war could end civilization. We have no backup. Mars is the only planet in our solar system that could support human life. It's our insurance policy. Stephen Hawking said, spreading out may be the only thing that saves us from ourselves. Why not the moon? The moon has no atmosphere, 14-day nights, no water ice in useful quantities, and gravity 1/6 of Earth's. Mars has a 24-hour day, a thin atmosphere, water ice in abundance, and 38% of Earth's gravity, low enough to make launches easy, high enough to raise healthy children. Mars has everything we need to survive: water ice to drink, to grow food, to split into hydrogen and oxygen for rocket fuel, carbon dioxide to grow plants, iron, aluminum, and silicon to build. Mars isn't just a destination, it's a home.
Starship is the largest rocket ever built. It stands 120 meters tall, taller than the Statue of Liberty. It weighs 5,000 tons fully fueled. Its 33 Raptor engines generate 16 million pounds of thrust. It can lift 100 tons to the moon, 100 tons to Mars, 100 tons anywhere. Its 33 Raptor engines generate 16 million pounds of thrust. This is the heart of the interplanetary transport system. Taller than any rocket in history, its scale is hard to comprehend until you see it against our greatest monuments. Built for one purpose, to make life multi-planetary, it is the most powerful rocket ever built. The key to Mars is reusability. Without it, the cost of space travel remains prohibitive. The Super Heavy booster lands back on Earth, precision-guided to its launch mount for rapid turnaround. Starship continues to orbit while the booster is already being prepared for its next flight. Starship lands on Mars, refuels, and flies back. Each ship can be used dozens of times. The cost per launch drops from billions to millions. Mars becomes affordable for the first time in history. Elon Musk notes, if Starship is fully reusable, the cost per launch drops to around $2 million. That makes Mars possible. Each Starship can carry 100 tons to Mars, a payload capacity that changes the nature of exploration. Inside are habitats, rovers, solar panels, and construction equipment, the building blocks of a new civilization. In each launch window, every 26 months, SpaceX plans to send 10 to 20 Starships. That's 1,000 to 2,000 tons of cargo per window, enough to build a city on another planet. To get to Mars, Starship needs to refuel in orbit. This is the critical step in the journey. A tanker Starship launches, docks with the crew Starship, and transfers propellant. It's a delicate dance in zero-G. It takes about 10 tanker flights to fully fuel one crew Starship. Once the tanks are topped off, the mission begins. Fully fueled and ready for the long journey ahead, then it's off to Mars. Our future among the stars begins now.
Mars and Earth only align for a Mars mission every 26 months. During these windows, Starships launch in waves. The journey takes about 6 months. Then the window closes and they wait for the next one. Starship is designed for 100 passengers, private cabins, exercise areas to maintain muscle and bone mass, common spaces to socialize, windows to watch the stars. For 6 months, this is home. The journey has dangers, cosmic radiation, microgravity. The ship has a storm shelter for solar flares. Passengers exercise 2 hours daily to maintain muscle and bone. By the time they arrive, they're ready to work.
Before the first humans arrive, cargo starships will land. They'll carry solar panels, habitats, rovers, and critical life support systems.
They'll land autonomously, preparing the site with robotic precision. When the crew finally arrives, their home and infrastructure are already waiting. The first starships land in a circle, creating a protected landing zone. Their cargo bays become the first storage units. Their fuel tanks become reservoirs. The ships themselves become the very first structures of the Martian base. The first crew lands. They step onto Martian soil for the first time in history. They've been training for years. Now the real work begins. They unload cargo and set up habitats. The foundations of the first city are laid. The first city has begun. Prepare for the next wave.
Starship can't return to Earth with fuel from Earth. The fuel is too heavy. It must be made on Mars. That's the key to the entire plan. If we can make fuel on Mars, starships can fly back. Mars becomes accessible. The Sabatier process combines carbon dioxide from the Martian atmosphere with hydrogen from water ice. It produces methane, the fuel Starship uses, and oxygen. The oxygen is used as oxidizer. Water is recycled. The propellant plant is the heart of the city. It produces fuel for starships. Each starship needs 1,000 tons of methane and oxygen. The plant runs on solar power. It produces fuel continuously. When the launch window opens, starships are ready.
The first habitats are inflatable. They're lightweight, compact for transport. Once deployed, they expand. A 3D printer then covers them with Martian soil, regolith, for radiation protection. Each habitat becomes a home. Mars has no magnetic field, no thick atmosphere. Radiation is a constant threat. The habitat's regolith shell provides protection, 2 to 3 meters of Martian soil above the living space. Inside, it's as safe as Earth. Future habitats will be underground. Mars has lava tubes, natural caverns formed by ancient volcanic activity. These provide natural radiation protection. We'll seal them, pressurize them, and build cities inside.
The Martian atmosphere is 95% carbon dioxide. A life support system extracts oxygen from CO2. It adds nitrogen from the atmosphere. The result is breathable air. Recycled, clean, always available. Mars has water ice in abundance, at the poles and buried beneath the surface at mid-latitudes. We drill, we melt, we filter. The water is pure. It's for drinking, for growing food, for making fuel. Food is grown in hydroponic greenhouses. Plants grow in nutrient-rich water, not soil. LED lights provide the perfect spectrum. The first crops: potatoes, lettuce, tomatoes, wheat. Within a few years, the colony is self-sufficient in food. Mars gets about half the sunlight Earth does. Solar panels work, but they're less efficient. And dust storms can cover them, cutting power for weeks. Solar is part of the solution, but not the whole solution. Dependency on the sun alone creates a vulnerability for a growing colony. We need a constant heartbeat of energy. NASA's kilopower reactor is designed for Mars. It's small, safe, and provides constant power. 10 kilowatts per unit. A cluster of reactors can power a whole city, providing a reliable energy baseline. Nuclear power works through dust storms, through the night, through anything the red planet throws at us. It is the unwavering foundation of the Martian power grid, ensuring energy storage is critical. Batteries store excess power from the day for heavy nighttime demand. Hydrogen produced from water can be burned for heat or used in fuel cells during emergency outages. This synergy of nuclear, solar, and storage creates a system that is redundant, reliable, and resilient. The Martian city doesn't just survive, it thrives on a power grid built to endure for generations.
The first wave is small, 100 people. They're engineers, scientists, medics, builders. Their job? Build the infrastructure, the propellant plant, the habitats, the greenhouses. They prepare for the next wave. Every 26 months, more starships arrive, thousands of colonists. The outpost becomes a settlement, a town. Streets, shops, schools. A new society begins to flourish under the Martian sky. By 2050, the city has 100,000 people. Sleek underground tunnels connect the sprawling habitats. Pressurized domes create outdoor spaces. Automated factories produce essential goods for the colony. Schools teach Martian-born children.
New accents. Earthlings and Martians might struggle to understand. Earthlings and Martians might struggle to understand each other.
Tense, dramatic voice. 4 months after Neil Armstrong took that one small step, America was ready to go back. Apollo 12 was supposed to be routine, the second moon landing, a demonstration that we could do this regularly. But the weather had other plans. As the Saturn V lifted off, it flew directly into a thunderstorm. 36 seconds later, lightning struck. Then it struck again. In mission control, every alarm went off. The capsule lost power, telemetry. For a terrifying moment, it seemed like the mission was over before it had truly begun. This is the story of Apollo 12, the mission that almost didn't make it, and the crew that refused to give up. The crew of Apollo 12 was different. Where Armstrong was reserved and professional, Pete Conrad was outgoing, irreverent, and funny. He'd made a bet with a reporter that he'd say something spontaneous when he first stepped on the moon, and he delivered. Dick Gordon was a naval aviator with ice in his veins. Al Bean was an artist at heart. He'd later become a painter. Together, they brought a new energy to space exploration. They'd need every bit of that attitude when things went wrong. Apollo 11's landing was historic, but it wasn't precise. Apollo 12 had a different goal, precision. Their target was Surveyor 3. If they could land within walking distance, they could retrieve parts from it. The first time humans visited an alien spacecraft. Launch day. The weather at Kennedy Space Center was terrible. Rain, low clouds, and storms building. The launch window was narrow. If they missed it, the mission would be delayed for months. The decision was made to go. The Saturn V could fly through rain, they reasoned. Lightning was a concern, but they didn't realize they might trigger it. At 11:22 a.m., the Saturn V roared to life and lifted off, climbing into the overcast sky. Rain lashed the windows. Inside, Pete Conrad, Dick Gordon, and Al Bean monitored their instruments, feeling the vibration of the most powerful machine ever built. 36 seconds after launch, the Saturn V triggered a lightning strike. The bolt hit the rocket and followed its plume. In the capsule, every warning light came on. Fuel cells dropped offline. In mission control, telemetry went dead. Al Bean later said, all of a sudden, the control panel just lit up like a Christmas tree. The spacecraft was trying to tell us something was wrong. Before anyone could react, a second lightning bolt struck. This one was even more damaging. The guidance platform was lost. The command module was running on backup power, and the Saturn V was still climbing, carrying them toward orbit with no rain. But one man, John Aaron, noticed something strange in the voltage readings. He remembered a pattern from a simulation months earlier. He said, "Flight, try SCE to aux." Aaron recalled, "It was just one of those things. I'd seen it in a simulation, and it stuck in my memory." In the capsule, Al Bean heard the call. He found the obscure switch and flipped it. Instantly, telemetry returned to normal. The fuel cells came back online. The spacecraft was alive again. They'd been saved by a 26-year-old's memory. I didn't know what the hell he was talking about, but Al found the switch, and John Aaron saved our mission. The lightning strikes were over, but their effects lingered. The spacecraft's guidance platform, the heart of its navigation system, was spinning uselessly. The crew would have to perform a manual realignment, using the stars to re-establish their orientation, a procedure they'd never practiced under these conditions. For the next few hours, the crew worked methodically, using a sextant to sight stars and feed their positions into the computer. It was like navigating an ocean ship in the 18th century, except they were traveling at 25,000 miles per hour, 250,000 miles from Earth. Slowly, painstakingly, they rebuilt their navigation solution. By the time they were ready for translunar injection, they had their orientation back. With navigation restored, it was time for the translunar injection burn, the critical engine firing that would send them to the moon. The SIVB stage fired for nearly 6 minutes, accelerating them to escape velocity. They'd survived the lightning. Now they had a mission to complete. As they left Earth behind, the crew took a moment to appreciate the view. No borders, no divisions, just one planet, one home. It's a view that changes everyone who sees it. Pete Conrad, never one for sentimentality, was quiet for a moment. Then he got back to work. 3 days after launch, they arrived at the moon. They were now in orbit around another world, only the second crew to achieve this feat. The service module engine fired for exactly the right duration, slowing them enough to be captured by lunar gravity. Somewhere down there, Surveyor 3 was waiting. For the next day, they orbited the moon, studying their landing site. The target was a spot in the Ocean of Storms, about 1,000 feet from Surveyor 3. It was the most precise landing target ever attempted. If they missed by even a few hundred feet, they'd be too far to walk to the robot. The moment came for separation. Pete Conrad and Al Bean floated through the tunnel into the lunar module, intrepid. They were on their own now. With a gentle push from Springs, they separated from the command module. Dick Gordon would stay behind while his crewmates descended. Powered descent initiation. The engine fired, slowing them from orbital velocity and beginning the long drop to the surface. Below, the moon rushed up at terrifying speed. Pete Conrad had his eyes on the landing site, ready to take manual control. Al Bean called out altitudes and velocities. They were aiming for a spot 1,000 feet from Surveyor 3, a precision landing. Landing on the moon is incredibly difficult. There's no GPS, no atmosphere. Intrepid's landing radar sent pulses toward the surface. The computer compared the data to preloaded maps, calculating the descent profile. Pete Conrad watched out the window. In the final seconds, dust erupted around them, a cloud of razor-sharp particles. Pete Conrad couldn't see the surface. He was flying blind, relying entirely on his instruments. But he'd trained for this. He trusted the computer, his crewmate, and the engineers. Then, contact. Probes touched the surface, signaling the engine to shut down. Dust settled. Silence returned. Pete Conrad looked out the window and saw exactly what he'd hoped to see. Surveyor 3, sitting quietly about 600 feet away. They'd hit their target with unbelievable accuracy. "Hey, there it is!" he exclaimed, "right where it's supposed to be!" When Pete Conrad stepped onto the moon, he remembered his bet with a reporter that he'd say something spontaneous. He grinned and said, "Whoopee, man, that may have been a small one for Neil, but it's a long one for me." Classic Pete Conrad. Al Bean followed soon after, becoming the fourth human to walk on the moon. He was overjoyed. This was the moment he'd dreamed of. Together, they set up the flag, took the obligatory photos, and got to work. There were experiments to deploy and samples to collect, but not everything went smoothly. Al Bean was setting up the color TV camera, supposed to broadcast live from the moon. In his excitement, he accidentally pointed it directly at the sun. The intense light burned out the sensor instantly. The feed died. Millions saw nothing but static. Bean was devastated. "I pointed it at the sun," he said. "I thought it would be okay, but it wasn't." But there was still work to do. Their primary goal was to reach Surveyor 3, about 600 feet away, a significant trek on the moon. When they reached Surveyor 3, they stood for a moment, taking it in. A robot from Earth waiting for them for 2.5 years. Working carefully, they removed components, the TV camera, the soil scoop. They bagged them to bring back to Earth, the ultimate salvage mission.
Out there in the vast darkness of the universe, nearly 2.5 million light-years away from Earth, lies a massive spiral galaxy, Andromeda. Bigger than our Milky Way, containing nearly 1 trillion stars, it is our closest galactic neighbor and our future destiny. Spanning approximately 220,000 light-years across, its majestic spiral arms are factories of star formation, burning with the light of new suns. At its heart lies a dense core, packed with ancient stars and a supermassive black hole exceeding the mass of our own sun by millions of times. It is not alone. Andromeda commands a fleet of satellite dwarf galaxies, like M32 and M110, caught in its immense gravitational pull. While most of the universe expands away from us, Andromeda is different. It is hurtling towards the Milky Way at 110 kilometers per second. In about 4.5 billion years, our two galaxies will meet in a cosmic dance of gravity, reshaping the night sky of any world watching. This will not be a destruction, but a merger. A new, massive elliptical galaxy will be born from the chaos, often called Milkomeda. The space between stars is so vast that individual collisions are unlikely, but the view from Earth would be a spectacular light show lasting millions of years. Until then, Andromeda remains a beautiful silent giant in our night sky, a reminder of the dynamic and ever-changing cosmos we call home.
What if we could see space-time? Not just imagine it in equations, not just trace it in diagrams, but see it, feel it, move through it. What would it look like? How would it behave? What secrets would it reveal? This is not a documentary about physics. This is more than just physics. This is an experience, a journey into the fabric of reality itself. We are all swimming in an ocean we cannot see. Every moment of our lives, we move through space-time. We are carried by it, shaped by it, bound by it. But we cannot perceive it directly. It is invisible, like a fish that cannot see the water it swims in. But what if we could? What if we could open our eyes to the fabric of reality itself? In this documentary, we will open those eyes. We will visualize space-time as it truly is. A dynamic, flowing, living fabric that bends around every particle of matter, that ripples with every cosmic collision, that carries us through the universe at the speed of light. We will see it around a star, around a black hole, around your own body. This is general relativity, made visible. For centuries, we saw the universe through Isaac Newton's eyes. Space was a vast, empty stage, fixed, absolute, unchanging. Time was a universal clock, ticking the same for everyone, everywhere. If you moved through space. Time just passed. Simple, intuitive, wrong. Absolute space in its own nature remains always similar and immovable. In Newton's universe, space was a rigid grid. You could travel anywhere, and the grid stayed the same. Time was a river flowing at a constant speed. Nothing could change them. This was the world we knew for 200 years. Then a young patent clerk in Switzerland had an idea that would shatter it. The cracks in Newton's universe appeared in the 19th century. Scientists noticed something strange. The speed of light seemed to be constant, no matter how fast you were moving. That shouldn't happen. If you shine a light from a moving train, shouldn't it go faster? It didn't. Something was wrong. Something was missing. Something was about to change everything.
In 1905, a 26-year-old Albert Einstein had a thought experiment. What would it be like to ride a beam of light? That question led him to a radical conclusion. The speed of light is constant for all observers. This simple idea had a mind-bending consequence. Time is not absolute. If you move very fast, time slows down for you. Einstein asked, "What would I see if I rode a beam of light?" If you travel at 90% of light speed, time slows by half. At 99.9%, it slows by a factor of 22. At 99.9999%, years on Earth pass like days for you. Time is not a universal river. It is a flexible fabric that can be stretched and compressed by motion. They are inextricably linked. Einstein realized that space and time were not separate. They were woven together into a single, four-dimensional fabric. He called it space-time. Every event in the universe has a location in space-time. 3 coordinates for space, 1 for time. You cannot move through space without moving through time. As Hermann Minkowski said, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve reality. To understand space-time, we use a simple analogy. Imagine a rubber sheet. Place a heavy ball on it. The sheet dips. That dip is gravity. A smaller ball rolls toward the larger one not because it's being pulled, but because it's simply following the curve of the sheet. Gravity is geometry. Einstein summarized it. Matter tells space-time how to curve. Space-time tells matter how to move. This is the essence of his vision. But space-time is not a 2D sheet. It is a 3D fabric that wraps around everything. A massive star creates a 3D warp in the space around it, and that warp is what we feel as gravity. If we could see space-time, this is what we would see. A star is not a point of light in empty space. It is a weight on the fabric of reality, bending it, warping it, and everything around it, planets, comets, light itself, is simply following those curves, exploring the impossible, one curve at a time. Some questions seem too big to answer. We answer them anyway. Join us as we unravel the mysteries of the universe.
Earth is not just a rock floating in space. It is a dent in the fabric of reality, a warp in space-time, and you are inside that warp. The sun's warp is enormous. Planets don't orbit because of a mysterious force. They are simply rolling along the curve of space-time like marbles in a funnel. If you could see space-time, you'd see that time is not uniform. Near massive objects, the fabric is stretched, and time itself flows slower. It's a fact.
A clock at sea level ticks slower than one on a mountain. Your head is actually slightly older than your feet. Now imagine a neutron star. Its warp is so extreme that time passes at half the rate. 1 year, there is 2 years elsewhere in the universe. Time dilation is not just science fiction, it is a fundamental fact of our universe. If we could see space-time, we would see it happening everywhere.
Some questions seem too big to answer. We answer them anyway. If we could see space-time around Earth, we would see something surprising. It is not uniform. Earth's gravity varies from place to place. Mountains create tiny warps. Ocean trenches create dips. The geoid, the shape of Earth's gravitational field, is a lumpy, uneven landscape of space-time. Every satellite in orbit is navigating this warp. They follow the curves like marbles rolling in a bowl. The orbits are not circles or ellipses in empty space. They are paths through curved space-time. GPS satellites have to account for both the warp of Earth and the time dilation of their motion. Earth's rotation does something even more subtle. It drags space-time with it. This is called frame dragging. As Earth spins, it twists the fabric of space-time around it, like stirring honey with a spoon. This effect has been measured by satellites. If we could see space-time, we would see Earth's warp slowly rotating. Now we come to the ultimate warp, a black hole. Here, space-time is stretched to its limit. Near the event horizon, the fabric is falling inward faster than light itself. Light can travel outward at the speed of light, but the fabric is moving inward even faster. So light cannot escape. The event horizon is the point of no return. Space-time is falling into the black hole faster than light. That's why nothing can escape. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. What you see is not the black hole itself, it is the silhouette of space-time warped beyond return. The glowing ring is light from matter heated to billions of degrees. This is what space-time looks like at its most extreme. If you fell toward a black hole, you would experience the ultimate expression of space-time curvature, spaghettification. The gravity at your feet would be much stronger than at your head. You would be stretched into a long, thin strand of matter. This is not a metaphor. This is what happens when space-time is stretched to its breaking point. Inside the event horizon, space-time becomes something else entirely. Time and space swap roles. What was space becomes time. What was time becomes space. The singularity at the center is where space-time ends, where our understanding ends, where the universe hides its deepest secrets.
If space-time is a fabric, then violent events should create ripples, gravitational waves. In 2015, scientists at LIGO detected these ripples for the first time. From two black holes merging 1.3 billion light-years away, if we could see space-time, we would see these waves passing through us constantly. LIGO scientists stated, "We have detected gravitational waves. We did it. Every moment, the fabric of space-time is being stretched and compressed by distant cosmic collisions. These waves are passing through you right now. The effect is tiny, smaller than a proton, but it is real. When two black holes merge, they release more energy in a fraction of a second than all the stars in the universe combined. That energy is not light, it is waves in space-time itself. They stretch and compress space as they pass. In the GW1 Fanvo 914 event, 3 solar masses were converted entirely into gravitational waves. If we could see space-time, we would see these ripples as clearly as waves on an ocean. The effect on Earth is smaller than a proton, but it means the universe is breathing. If we could see space-time on the largest scale, we would see the cosmic web. The distribution of galaxies is not random. They cluster along filaments of dark matter, and those filaments warp space-time. The universe is not a flat, empty void. It is a complex, curved landscape of peaks and valleys, hundreds of millions of light-years across. Our own local group is being pulled toward a region called the Great Attractor. Something massive is warping space-time. Galaxies are flowing toward it like water down a drain. We cannot see it directly, but its warp is unmistakable. On the largest scale, the shape of space-time determines our fate. Is it flat, like a sheet? Is it positively curved, like a sphere, where traveling in a straight line brings you back? Or is it negatively curved, like a saddle? Measurements show it is nearly flat, but the answer is not yet certain. Some questions seem too big to answer. We answer them anyway.
At the smaller scales, the Planck scale, a trillion times smaller than a proton, space-time is not smooth. It is a frothing, bubbling foam. Quantum create and destroy tiny bubbles of space-time. This is the quantum foam. If we could see space-time at this scale, we would see a universe in constant flux. The scales here are unimaginable. The Planck length, 1.6 is 10 to 35 meters. It is the smallest possible unit of distance. And Planck